What if the universe is not only more mysterious than we can imagine, but also far more terrifying with each new discovery? Every day, scientists unveil groundbreaking revelations that challenge our understanding of reality, revealing dark and enigmatic forces at play. Concepts like dark matter and dark energy, which together make up an astonishing 95% of the universe, yet remain hidden from our view. This vast, unseen portion of the cosmos continues to elude our grasp, forcing us to reconsider everything we thought we knew about the very fabric of existence. Join us as we embark on a journey to explore some of the most unsettling discoveries ever made in the realm of space. First, we delve into the dark matter, an elusive substance that constitutes roughly 27% of the universe. Unlike ordinary matter, which is made up of atoms and is visible in the form of stars, planets, and galaxies, dark matter does not emit, absorb, or reflect light. This unique characteristic renders it invisible, making it impossible to detect with telescopes or any of the conventional tools we've relied upon for centuries. Instead, its presence is inferred through its gravitational effects on visible matter, an invisible influence that shapes the very structure of the universe. The idea of dark matter began to take shape back in the 1930s, thanks to the pioneering work of astronomer Fritz Zwicky. As he studied galaxy clusters, Zwicky was struck by a strange anomaly. While analyzing the Coma cluster, he discovered that the visible matter alone could not account for the observed motion of the galaxies within it. The galaxies were moving at speeds that seemed to defy the laws of physics, far too fast to be explained by the gravitational pull of the visible matter alone. This led Zwicky to propose the existence of what he called missing mass, a concept that would later evolve into the theory of dark matter. His discovery marked the first significant indication that unseen forces were at work in the universe. Forces that were influencing cosmic dynamics in ways we had yet to comprehend. In the years that followed, more evidence emerged to support the dark matter hypothesis. In the 1970s, astronomer Vera Rubin made a groundbreaking observation. While studying the rotation speeds of galaxies, she found something unexpected. Instead of decreasing as one would expect based on the mass visible within a galaxy, the stars at the outer edges of galaxies were moving at velocities much higher than anticipated. And this anomaly could only be explained by the presence of a vast, unseen mass, dark matter, extending far beyond the visible edges of the galaxy, exerting a gravitational pull that influenced the motion of the stars. The rotation curves of spiral galaxies revealed that dark matter was not only abundant but essential in explaining how galaxies maintain their shape and stability. Today, the search for dark matter continues to captivate the scientific community. Researchers and physicists have put forward several possible candidates to explain this mysterious substance, including weakly interacting massive particles, WIMPs, and other exotic forms of matter. Countless experiments and studies are ongoing, attempting to pinpoint what dark matter truly is and how it interacts with the rest of the universe. Despite our growing understanding of its gravitational influence, the fundamental nature of dark matter remains one of the greatest unsolved mysteries in science. Dark matter plays a vital role in the formation and structure of galaxies. Unlike ordinary matter, which gives rise to stars, planets, and even life itself, dark matter remains invisible and undetectable through conventional means. However, its presence is crucial to the formation of galaxies. When galaxies begin to form, they do so within enormous clouds of dark matter. This hidden mass exerts a powerful gravitational pull, drawing ordinary matter together and helping to kickstart the creation of stars and galaxies. Without this invisible scaffolding, galaxies would be unable to maintain their shape, their movements, or their very existence. As galaxies evolve, dark matter continues to shape their destiny. It helps stabilize the structure of galaxies and governs their motion. One of the most striking pieces of evidence for the influence of dark matter comes from the study of spiral galaxies. When scientists observe the rotation curves of these galaxies, they notice a strange phenomenon. The stars at the outer edges of the galaxy are rotating much faster than would be expected based on the visible mass alone. This discrepancy can only be explained by the additional mass provided by dark matter, which extends well beyond the visible boundaries of the galaxy. This unseen matter helps to bind galaxies together, ensuring that they do not fly apart as they spin. The mystery of dark matter is far from solved, but one thing is clear. It is fundamental to the structure and behavior of the universe. It is the hidden force that holds galaxies together, shapes their movements, and governs the cosmos on a scale that is nearly beyond our comprehension. As scientists continue to search for answers, the enigma of dark matter serves as a reminder that the universe is far more complex and far more terrifying than we could ever have imagined. Dark matter plays an essential role in shaping the structure and distribution of galaxies across the vast expanse of the universe. Galaxies are not isolated entities, but are found clustered together in vast structures known as galaxy clusters. These clusters, often massive collections of hundreds or even thousands of galaxies, are thought to be bound together and held in place by immense quantities of dark matter. This invisible substance exerts a gravitational influence that is so profound that it governs the formation, evolution, and interaction of these galactic clusters, especially during events like mergers and collisions. In this sense, dark matter is not just a passive player, but a driving force in the grand narrative of the universe. It helps to shape the structure of the cosmos, influencing the distribution and motion of galaxies on cosmic scales. It holds them together, preventing them from flying apart under the influence of gravity, and plays a significant role in their interactions and growth over billions of years. The mystery of dark matter, however, remains one of the most intriguing challenges in modern astrophysics, prompting scientists to explore a wide range of theories that go beyond what we can observe directly. Understanding dark matter could be the key to unlocking a deeper comprehension of the processes behind galaxy formation, the evolution of cosmic structures, and the fundamental forces that govern the universe itself. Scientists continue to probe the unseen, attempting to decipher the nature of this elusive substance and its interaction with the visible universe. The universe, as we understand it, is largely made up of two mysterious and largely unknown components: dark matter and dark energy. Despite their differing roles and properties, both make up approximately 94% of the total mass energy content of the universe. Dark matter accounts for about 27%, and its function is vastly different from that of dark energy, which constitutes roughly 73%. Both play critical roles in shaping the cosmos, yet both remain undetectable by traditional means of observation. Dark matter is often described as the invisible glue of the universe. It does not emit, absorb, or reflect light, making it completely invisible to our most advanced instruments. Its presence can only be inferred through its gravitational effects on visible matter, such as stars and galaxies. A striking example of this is the rotation curves of galaxies. If only the visible matter in a galaxy were considered, stars at the outer edges of galaxies should be flying off into space, as the gravitational pull from the visible matter wouldn't be enough to hold them in orbit. Yet the stars remain bound, suggesting the existence of dark matter, which provides the necessary gravitational pull to keep these stars in place. In contrast, dark energy acts in a radically different way. Whereas dark matter attracts matter, dark energy appears to repel it. This mysterious force is responsible for driving the accelerated expansion of the universe. The discovery of dark energy radically transformed our understanding of cosmic dynamics, revealing that not only is the universe expanding, but the rate of that expansion is also accelerating. This accelerating expansion is one of the most perplexing and revolutionary findings in modern cosmology, reshaping our understanding of the universe's ultimate fate. Dark energy's properties remain a subject of intense debate among scientists. It is often modeled as a constant energy density that permeates space, pushing galaxies apart. Some researchers propose that dark energy is a property of space itself, often referred to as the cosmological constant, a concept introduced by Albert Einstein. Others suggest alternative theories, including dynamic fields that evolve over time. Despite the various hypotheses, the existence of dark energy is undeniable, and it highlights the vastness of what we still do not understand about the fabric of the universe. Together, dark matter and dark energy form the backbone of the cosmos, yet they remain hidden from direct observation. They shape the universe in ways we are only beginning to understand. The gravitational effects of dark matter hold galaxies together, while dark energy drives the universe's accelerated expansion. The interplay between these two components is at the heart of the mystery that surrounds the universe's large-scale structure. The study of dark matter and dark energy was revolutionized in the late 20th century with the discovery that the universe's expansion is accelerating. This was first observed through the study of distant Type Ia supernovae. These stellar explosions are among the brightest objects in the universe, serving as cosmic beacons that allow astronomers to measure vast distances. When scientists studied these supernovae, they found that they were dimmer than expected, suggesting that they were farther away than previously thought. This dimming effect could only be explained by the realization that the expansion of the universe was not just ongoing, but accelerating. The most plausible explanation for this accelerated expansion is the presence of dark energy. Further support for the existence of dark energy came from studies of the cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang. Observations of the CMB, particularly from the Wilkinson Microwave Anisotropy Probe (AP) and the Planck satellite, revealed minute temperature fluctuations across the sky. These fluctuations provide a snapshot of the early universe, allowing scientists to understand its composition. Analysis of these fluctuations indicates that dark energy accounts for about 70% of the universe's total energy density, a finding that reinforces the idea of an accelerating universe. Another critical piece of evidence for dark energy comes from large-scale galaxy surveys, which map the distribution of galaxies throughout the universe. These surveys have revealed that galaxies are not randomly scattered, but are instead arranged in patterns that suggest the influence of dark energy. The repulsive force attributed to dark energy appears to be shaping the overall distribution of galaxies, influencing their clustering on the largest scales. By examining the gravitational effects of dark matter and contrasting them with the expansion driven by dark energy, scientists have pieced together a picture of the universe's evolution. The data consistently supports the idea that dark energy is essential to explaining the current rate of cosmic expansion and the large-scale structure of the universe. The mysteries of dark matter and dark energy continue to captivate and challenge scientists, who are racing to develop new theories and experiments that will help unlock their secrets. As we continue to explore these enigmatic components, we uncover more about the extraordinary complexity of the universe, its origins, its growth, and the fundamental laws that govern its behavior. The journey to understand these dark forces promises to reshape our view of the cosmos and our place within it. The discovery of gravitational waves has brought forth a wealth of new evidence, further cementing the hypothesis of dark energy's existence. These ripples in the fabric of space-time, detected for the first time in 2015, have proven to be more than just ripples in the cosmic ocean. They offer an entirely new way to observe how the universe's expansion is shaping its very structure. Gravitational waves are a unique tool, allowing scientists to peer into the unseen forces that drive the cosmos. As researchers study the patterns of light and gravitational waves, they gain vital insight into the dynamics of cosmic events, many of which are influenced by the mysterious force of dark energy. The data extracted from these emissions reveals important clues about the ways in which dark energy shapes both the past and future of the universe. Collectively, the evidence for dark energy is growing stronger with each new discovery. These observations, from the rippling effects of gravitational waves to the behavior of light across the vast expanses of space, offer a comprehensive view of how dark energy impacts the universe. Theories about its nature are still in flux, but the accumulating data offers a compelling framework that supports its existence. As our understanding of dark energy deepens, so too does our ability to grasp the grand tapestry of the universe, from its origins to its ultimate fate. On the other side of the cosmic puzzle lies dark matter, a substance that remains one of the most enduring enigmas in astrophysics. While dark energy is thought to drive the universe's accelerated expansion, dark matter is the unseen glue that holds galaxies, clusters, and even the universe itself together. Direct detection of dark matter remains elusive. However, scientists have found compelling indirect evidence that hints at its existence. Unlike visible matter, dark matter neither emits nor absorbs light, making it invisible to traditional astronomical instruments. Despite this, its gravitational effects on the visible universe provide scientists with critical clues. Perhaps the most telling evidence of dark matter's existence comes from the rotation curves of galaxies. These curves show that galaxies are spinning much faster than would be expected if they only contained the visible matter we can observe. If only stars and gas were present, the outer edges of galaxies should fly apart due to the centrifugal force generated by their rotation. Yet they don't. This discrepancy suggests that an unseen mass, dark matter, must be exerting a gravitational pull strong enough to hold the galaxies together. The faster than expected spins point to a significant, invisible presence within galaxies. Further support for dark matter comes from studying the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. Fluctuations in temperature within the CMB offer a map of the universe's earliest moments. These variations suggest that the distribution of matter and energy in the early universe, including the unseen presence of dark matter, shaped the development of cosmic structures. By studying the CMB, scientists have been able to infer that dark matter makes up a substantial portion of the universe's total mass and energy content. The phenomenon of gravitational lensing also provides key insight into the distribution of dark matter. When light from distant galaxies passes near a massive object, such as another galaxy or cluster of galaxies, it bends around the object due to its gravitational field. This bending can be used to map out the distribution of both visible and invisible mass in the universe. By studying these lensing effects, scientists can observe how dark matter is distributed, revealing its pervasive influence on the structure of the cosmos. While the indirect evidence is compelling, scientists are still striving to detect dark matter directly. To do this, research teams around the world are developing highly sensitive detectors. These devices are often placed underground or in remote locations to shield them from cosmic radiation and other background noise that might interfere with the delicate measurements. So far, no one has successfully detected dark matter particles, but the search continues. As technology advances, there remains hope that one day we will capture the elusive particles that constitute dark matter and unlock one of the greatest mysteries of modern science. The potential discovery of dark matter would not only confirm many of the existing theories in cosmology, but it would also profoundly alter our understanding of the universe. Ordinary matter, such as the stars and planets we can see, makes up only a small fraction of the universe's total content. Dark matter, however, is believed to account for about 24% of the universe's mass energy content, a staggering amount that dwarfs the visible matter we observe. This invisible substance, which interacts only through gravity, has been a critical force in shaping the formation of galaxies, stars, and other cosmic structures. If scientists can finally detect dark matter particles directly, it would provide a deeper understanding of the forces that govern the universe. Moreover, such a discovery could have far-reaching implications for fields as diverse as particle physics, cosmology, and even philosophy. What is dark matter? How does it interact with the forces that we know and understand? These questions could reshape our perception of reality itself. Dark matter is not only an interesting puzzle in itself, but it also holds the potential to unlock deeper secrets of the universe. Understanding its properties might allow scientists to explore other cosmic phenomena, such as dark energy, which is responsible for the accelerating expansion of the universe. The quest to understand dark matter and dark energy is crucial because it connects directly to the future of the universe and its ultimate fate. While researchers have made significant strides in understanding dark matter, its true nature remains elusive. Several theories have emerged in attempts to explain what dark matter could be made of. One of the most widely discussed ideas is that dark matter is composed of weakly interacting massive particles, or WIMPs. These hypothetical particles are thought to be heavy and interact very weakly with normal matter, making them extremely difficult to detect with current technology. Despite extensive efforts, no WIMPs have been observed directly, leaving the question of dark matter's composition wide open. Another intriguing possibility is that dark matter could consist of axions, extremely light particles that may have been created in large numbers during the early moments of the universe. Axions would interact very weakly with normal matter, making them virtually undetectable through standard methods. However, their role in the universe's formation and their potential contribution to dark matter could be profound. The search for axions is currently underway, with scientists attempting to create conditions in laboratory settings where these particles might be detected. If either WIMPs or axions, or perhaps an entirely different class of particles, turn out to be the true constituents of dark matter, it would not only solve one of the most significant problems in modern science, but it would also provide new insights into the fundamental workings of the universe. Understanding dark matter's true nature would give us a deeper understanding of the cosmos itself and how all the forces of nature work together to shape reality. The hunt for dark matter is just beginning. As we develop better detectors, more advanced technologies, and more refined theories, we will continue to push the boundaries of our knowledge. Every discovery, every piece of evidence brings us one step closer to solving one of the universe's most profound mysteries. Some scientists are exploring the intriguing possibility that primordial black holes formed shortly after the Big Bang could make up a significant portion of dark matter. These black holes, if they exist, would be incredibly difficult to detect. Unlike conventional black holes, which emit radiation or interact with their surroundings, primordial black holes would not emit any light. They would only interact through gravity, making their detection an extremely challenging task. If this theory holds true, it could drastically reshape our understanding of dark matter and the evolution of the universe itself. Yet, the quest to understand dark matter doesn't end there. While primordial black holes are a compelling hypothesis, alternative theories exist that aim to explain the phenomenon without the need for unseen particles. Modified gravity theories, such as modified Newtonian dynamics, MND, propose that the laws of gravity might be altered on cosmological scales. These theories attempt to explain the same gravitational effects that dark matter is thought to account for, but without invoking the existence of unknown particles. Each of these ideas, whether primordial black holes, modified gravity, or another hypothesis, offers a unique perspective on how we can examine the universe. Researchers continue to test and explore these theories, hoping to reveal the true nature of dark matter. With advancements in technology, our ability to investigate these mysteries is growing, and researchers are optimistic that new discoveries are on the horizon. The exploration of dark matter and dark energy is on the brink of a revolution, fueled by advancements in technology. These two mysterious components are central to understanding the cosmos, yet remain shrouded in uncertainty. As our observational tools become more advanced, our capacity to study the universe's hidden forces grows exponentially. Cutting-edge telescopes and instruments equipped with advanced optics and sensors are being developed to capture more sensitive, detailed observations than ever before. These tools can detect faint signals and anomalies that might be linked to dark matter, either through its gravitational effects or its subtle interactions with ordinary matter. The rise of computational power has opened new avenues for studying these cosmic phenomena. Modern simulations can process vast amounts of astronomical data with remarkable speed and precision, enabling scientists to generate insights more quickly than ever before. Artificial intelligence, AI, and machine learning algorithms are now being employed to sift through these complex datasets, helping researchers identify patterns and anomalies that may be associated with dark matter and dark energy. AI can even predict the behaviors of these phenomena, which in turn leads to a deeper understanding of how they influence the structure and expansion of the universe. Meanwhile, the field of particle physics is taking great strides in the direct detection of dark matter. Underground laboratories and particle accelerators are becoming increasingly sensitive thanks to technological advancements, allowing scientists to probe the properties of potential dark matter candidates, such as weakly interacting massive particles, WIMPs. These experiments are pushing the limits of our knowledge and could eventually provide the breakthrough needed to understand the true nature of dark matter. Furthermore, the importance of interdisciplinary collaboration cannot be overstated in the pursuit of understanding dark matter and dark energy. Researchers from diverse fields such as astrophysics, cosmology, computer science, and engineering are working together to devise innovative solutions to these cosmic puzzles. By combining their expertise, they are developing novel strategies that offer new insights into the universe's most elusive components. As technology continues to advance and our collective understanding deepens, we move closer to solving some of the universe's most profound mysteries. Dark energy, the mysterious force thought to be driving the accelerated expansion of the universe, has profound implications for the fate of the cosmos. Current observations suggest that dark energy constitutes around 70% of the universe, yet its true nature remains one of the greatest enigmas in modern science. If dark energy continues to act as it does now, the universe will expand at an ever-accelerating rate. This relentless expansion will push galaxies further and further apart, leading to a scenario known as the Big Freeze. Over trillions of years, stars will exhaust their nuclear fuel and the universe will grow darker and colder. In this future, galaxies will drift beyond the observable universe, leaving isolated stars and planets scattered across an increasingly desolate cosmic landscape. But the future may not be set in stone. If dark energy changes or evolves in its properties, we could witness alternative outcomes. One possibility is that the expansion of the universe could slow down, allowing gravitational forces to regain control. This shift could lead to dramatic scenarios such as the Big Crunch, where the universe collapses in on itself. Such a collapse would not only alter the fate of the universe, but also challenge our most fundamental understanding of physics. The mysteries surrounding dark energy extend beyond its influence on the fate of the universe. They also invite deeper philosophical questions about the very fabric of space and time. Understanding dark energy could unlock answers to questions humanity has pondered for centuries, potentially reshaping our view of the universe and our place within it. As research continues and technology advances, we inch closer to unveiling the secrets of dark energy, which could ultimately change the trajectory of scientific thought for generations to come. In parallel, there have been significant breakthroughs in the study of dark matter. For decades, this mysterious substance has eluded direct detection, yet we know it constitutes roughly 27% of the universe's total mass. Recent experiments have made important strides in understanding dark matter's elusive nature, particularly through particle physics and astrophysics. One notable avenue of exploration has been the use of advanced particle colliders. For example, researchers at the Large Hadron Collider have been probing for particles predicted by theories beyond the standard model of particle physics. These discoveries may point toward potential dark matter candidates, such as weakly interacting massive particles, WIMPs, which remain undetectable due to their minimal interaction with ordinary matter. Despite the challenges in detecting dark matter, these ongoing efforts are crucial. The hunt for dark matter is no longer a theoretical pursuit, but an active area of investigation. With each experiment and discovery, we edge closer to answering one of the most fundamental questions about the universe. What is dark matter, and how does it shape the cosmos? As our knowledge grows, so too does our capacity to understand the hidden forces that govern the universe. The cosmos, vast and unfathomable, continues to surprise us with its endless mysteries. Among the many phenomena that have captured the collective imagination of scientists and astronomers alike, dark matter stands out as one of the most elusive and intriguing. Despite being invisible and detectable only through its gravitational influence on visible matter, dark matter shapes the universe in profound ways. Through the aid of increasingly advanced observational tools, such as the powerful telescopes that span our planet and even stretch into space, we've come to learn a great deal about the distribution and behavior of dark matter. One of the most critical breakthroughs in this field has come through the phenomenon of gravitational lensing. Gravitational lensing occurs when massive objects, such as galaxy clusters or black holes, bend and warp space-time, causing light from more distant objects to curve around them. This distortion not only acts as a magnifying glass, but also provides a map of dark matter's presence. By observing the light from distant galaxies, astronomers can infer the distribution of dark matter in the regions surrounding them. The Dark Energy Survey, along with the UCLID Space Telescope mission, stands poised to provide unprecedented insights into the very fabric of the universe itself. These surveys promise to reshape our understanding of dark matter, pushing the boundaries of knowledge further than ever before. As technology advances, so too does our comprehension of the universe. New methodologies and instruments allow scientists to peer deeper into space, revealing the inner workings of dark matter and potentially altering long-standing theories that were once considered absolute. The search for dark matter is far from over. Rather, it stands as a testament to science's evolving nature as new tools continuously challenge what we think we know, urging scientists to go further into the unknown to unearth the fundamental truths of the cosmos. Equally captivating, though perhaps even more mysterious, are black holes, celestial objects that evoke a sense of awe and wonder. A black hole is born when a massive star reaches the end of its life cycle. Once a star runs out of fuel, its core becomes unstable and collapses under its own gravity. This gravitational collapse continues until the core is compressed into a point of infinite density, creating a region where not even light can escape. This point of no return is known as the event horizon, the boundary that separates the black hole's interior from the outside universe. Once anything crosses this threshold, whether matter, light, or radiation, there is no escape. The size of the event horizon depends on the black hole's mass. It can range from a few times the mass of our sun to millions or even billions of times greater. Supermassive black holes, which reside at the centers of galaxies, including our own Milky Way, are among the most massive entities in the universe. Black holes are not only formed from the remnants of stars. Another fascinating way they can form is through the merger of two neutron stars, dense, compact objects left behind after a supernova explosion. When two neutron stars spiral inwards and collide, they can create a black hole and release an extraordinary amount of energy, detectable as gravitational waves. This collision, which takes place far beyond our reach, is not just the birth of a black hole, but also the unleashing of a cosmic event that ripples through space-time itself. For centuries, black holes have challenged our understanding of physics. These strange objects warp space-time in such a profound way that they force us to rethink the very nature of reality. In Einstein's theory of general relativity, gravity is not an invisible force, but a distortion of space-time caused by mass. A black hole, then, can be imagined as a point in space where gravity is so intense that it bends the very fabric of space and time. Objects that approach a black hole experience the warping of time itself. Time appears to slow down dramatically as they draw closer to the event horizon. If an observer were to watch an astronaut fall into a black hole, they would see the astronaut's descent slow to a crawl until they eventually fade from view as they cross the event horizon. The effects of a black hole on space-time are not limited to time dilation. They also create intense gravitational fields that pull surrounding matter into a swirling disk known as the accretion disk. As matter is drawn towards the black hole, it heats up, emitting brilliant radiation. This radiant energy can escape into space, providing a glimpse into the otherwise hidden black hole. These powerful jets of particles, which shoot far into space, extend the influence of the black hole well beyond its immediate vicinity. Even more fascinating is the ability of black holes to distort the trajectory of light itself, a phenomenon known as gravitational lensing. When light from stars behind a black hole is bent by its gravitational pull, the result is a distorted, magnified image that provides scientists with crucial insights into the universe's structure. These distorted images help astronomers study distant galaxies and other cosmic structures that would otherwise be obscured by the black hole's immense gravitational force. The event horizon, the very point that marks the black hole's boundary, remains one of the most enigmatic features of these celestial giants. As an imaginary surface, the event horizon represents a threshold that nothing can cross in the opposite direction. Once an object crosses this boundary, it is inexorably drawn into the black hole, unable to escape the crushing gravitational forces. Yet, this boundary has become more than just a physical location. It is a philosophical and scientific puzzle that challenges our understanding of space, time, and reality itself. The event horizon is key to many fundamental questions in physics. The laws of quantum mechanics dictate that information cannot be destroyed, yet when something crosses the event horizon, it seems to vanish from our universe. What happens to the information contained within objects that fall into a black hole? This paradox has sparked intense debate among physicists and has given rise to theories that challenge our conventional views of the cosmos. Some believe that information is not lost, but rather encoded on the surface of the event horizon itself, a theory known as the holographic principle. As we continue to explore the strange and mysterious properties of black holes, our understanding deepens. Matter that accumulates around the event horizon forms an accretion disk, which, when interacting with the black hole's immense gravity, emits radiation and energy that scientists can detect. These interactions allow astronomers to study black holes indirectly, unveiling the secrets of these enigmatic regions of space. Each new discovery about black holes brings us one step closer to understanding the fundamental laws that govern the universe itself. The mysteries of black holes and dark matter remind us of the vastness of the universe and how much we have yet to discover. With each breakthrough, our grasp of the cosmos expands, and the seemingly impenetrable voids of space begin to reveal their secrets. The search for answers continues, pushing the limits of human knowledge and technology, compelling scientists to explore deeper, to ask bigger questions, and to strive for a greater understanding of the universe's intricate workings. As we peer into the depths of space and time, we are reminded that the cosmos is far more complex than we can imagine, and every new discovery only deepens the mystery of it all. Black holes, those enigmatic giants of the universe, evoke a complex mixture of fascination and fear in those who dare to explore their mysteries. Much of the awe and anxiety surrounding black holes can be attributed to the myriad misconceptions that cloud our understanding of them. For instance, one of the most persistent myths is the notion that black holes behave like colossal vacuum cleaners, indiscriminately devouring everything in their vicinity. In truth, the gravitational pull of a black hole operates much like that of any other massive object, such as a planet or a star. If our sun were to suddenly transform into a black hole, Earth would continue orbiting it safely, as long as we did not venture too close. The strength of the sun's gravitational pull would remain the same, and our planet's path would remain unchanged. The only difference is that Earth would no longer receive light from the sun, an altogether different issue. Another myth that adds to the mystique is the belief that black holes are cosmic prisons where matter is obliterated, disappearing entirely from the universe. In reality, while a black hole traps everything that crosses its event horizon, the point beyond which nothing can escape, the matter inside the black hole is not lost to the cosmos. Instead, it becomes part of what is known as a singularity, a point of infinite density where our understanding of physics breaks down. The matter itself is transformed, but it is not annihilated in a way we can fully comprehend with current scientific knowledge. The idea that matter vanishes is a simplification. The truth is far more complex and nuanced, leaving us with more questions than answers. Equally unsettling is the fear that black holes are lurking throughout space, waiting to unleash their deadly grasp on unsuspecting planets like ours. While it is true that there are likely many undetected black holes scattered across the universe, they are not the menacing cosmic predators we often imagine. The nearest known black hole to Earth, for example, is located far enough away that it poses no threat to our planet. Black holes are incredibly distant, and given their nature, the odds of one ever approaching Earth in any dangerous manner are astronomically low. The universe, while vast and filled with these enigmatic objects, is more expansive than it might seem, and our planet is safe from such distant forces. A common misconception, too, is the belief that once an object falls into a black hole, it is doomed to remain there forever, with no possibility of escape. However, recent advances in theoretical physics have led scientists to consider the possibility that information falling into a black hole may not be completely lost. This idea, known as the black hole information paradox, suggests that while the exact mechanisms remain a mystery, it is possible that some form of information could eventually escape. How this might occur remains one of the most intriguing puzzles in the realm of modern physics, but the prevailing belief is that black holes are not the absolute dead ends they once seemed to be. These misconceptions point to a broader need for a more nuanced understanding of black holes, phenomena that continue to challenge our most basic assumptions about space, time, and the very fabric of our universe. The more we learn about these cosmic titans, the more we realize that they are not just strange anomalies, but key players in the grand story of the cosmos. Particularly intriguing are supermassive black holes, which reside at the centers of most large galaxies, including our own Milky Way. These gargantuan entities can have masses ranging from millions to billions of times that of our Sun, and their gravitational influence is so immense that they can alter the orbits of stars and clouds of gas within their reach. The role of supermassive black holes in the formation and evolution of galaxies cannot be overstated. They act as gravitational anchors, helping to maintain the structure of the galaxy. As matter falls into these black holes, it releases vast amounts of energy in the form of radiation. This energy can create powerful jets and winds that expel gas from the central regions of the galaxy. Interestingly, this expelled gas plays a crucial role in the birth of new stars, as it influences the amount of material available for star formation. Depending on the dynamics of the surrounding gas and the black hole's activity, these cosmic giants can either stimulate or stifle star formation, shaping the patterns of stellar birth across the galaxy. Moreover, supermassive black holes are not static entities. Their presence affects the overall dynamics of their host galaxies, influencing the movement of stars in the galactic core and creating complex gravitational interactions that unfold over time. When galaxies collide and merge, the black holes at their centers may experience a feeding frenzy, drawing in vast amounts of gas that further fuel their growth. This continuous process of interaction and evolution highlights a symbiotic relationship between galaxies and their central black holes. As galaxies evolve, so too do the black holes that reside within them, and this mutual influence shapes not only the structure of the galaxy, but also the fate of the stars that call it home. In this way, black holes are not just passive remnants of cosmic history, but active participants in the ongoing dance of galactic formation and transformation. One of the most dramatic and unsettling aspects of black holes is the phenomenon known as spaghettification. This term refers to the extreme stretching and elongation of objects that venture too close to a black hole, an effect caused by the immense differences in gravitational force that occur over short distances. As an object falls toward a black hole, the gravitational pull on the part of the object closest to the black hole is vastly stronger than the pull on the far side. This causes the object to be stretched vertically while simultaneously being compressed horizontally, leading to a stretching effect reminiscent of spaghetti. The closer the object gets to the black hole, the more extreme the spaghettification becomes. This is a vivid and terrifying illustration of the immense forces at work near a black hole. At the heart of this process is the event horizon, the point of no return. Once an object crosses this boundary, it is irrevocably drawn into the black hole's grip, unable to escape. Even light, which travels at the fastest speed in the universe, cannot break free from the black hole's gravitational pull once it passes the event horizon. The forces that cause spaghettification are known as tidal forces, and they arise from the steep gradient of gravity near the black hole. The difference in gravitational pull across such a short distance is so sharp that it results in an extreme stretching of any object that dares to come too close. While black holes have long been a source of fascination in both science fiction and scientific circles, spaghettification is a stark reminder of the dangers that await anything that ventures too near. These violent forces reveal the true nature of black holes, not as mysterious but alluring phenomena, but as dangerous cosmic giants that could easily tear apart anything unfortunate enough to approach too closely. Yet in this dangerous dance lies the core of our curiosity. How far can human exploration push before we encounter the limitations of our technology and understanding of the universe? Black holes may not just be the ultimate cosmic puzzle. They may also represent the ultimate challenge for human exploration, forcing us to confront the very boundaries of what we can know and what we can endure in our quest for knowledge. Black holes, those cosmic anomalies that defy our understanding of the universe, possess an extraordinary power that challenges our very grasp of physics. These enigmatic entities serve as the ultimate extreme of gravitational forces, where the fabric of space and time is twisted beyond our wildest comprehension. The phenomenon of spaghettification, a process where matter is stretched into thin strands as it approaches a black hole, captures this radical divergence from the normal laws of physics. It transforms a seemingly abstract concept into a vivid, almost terrifying image, underscoring the terrifying reality of the forces lurking in the darkness of space. It's a reminder that the universe, in all its awe-inspiring vastness, operates under rules far beyond what we are accustomed to. While the most famous black holes, stellar and supermassive, often dominate our imaginations, the universe is home to an array of equally perplexing varieties of these dark entities. One particularly intriguing class is the intermediate black hole, which exists somewhere between the mass of a stellar black hole and that of a supermassive one, with masses ranging from a few hundred to several 100,000 times that of our Sun. Intermediate black holes raise vital questions about their formation. Could they arise from the merging of stellar black holes, or perhaps the collapse of massive gas clouds? Theories are still evolving, and the true origin of these cosmic giants remains a topic of intense debate and study. Another fascinating category is that of primordial black holes, hypothetical objects believed to have formed within the first few moments of the universe's existence, just after the Big Bang. Unlike their stellar cousins, which are born from the death throes of massive stars, primordial black holes could span a wide range of sizes, from extremely small objects, perhaps even subatomic in scale, to those that are incredibly massive. These primordial relics of the early universe offer a tantalizing glimpse into the conditions that prevailed at the dawn of time. Their potential existence challenges our understanding of cosmic evolution, offering profound questions about the very fabric of the universe itself. Then there is the mysterious and speculative concept of ultramassive black holes. These colossal objects, thought to possess masses greater than 10 billion times that of our Sun, are typically found at the centers of the largest galaxies. However, their formation mechanisms remain an enigma. How could such vast black holes accumulate so much mass? Their size and power surpass our current understanding of how supermassive black holes grow over time. Moreover, their role in galaxy formation remains elusive, adding yet another layer of complexity to the already bewildering field of black hole physics. As scientists continue their exploration of the cosmos, the classification of black holes continues to evolve. Each newly discovered type broadens our knowledge and challenges the limits of what we understand about gravity, cosmic evolution, and the very structure of the universe. These discoveries push the boundaries of our comprehension, urging us to rethink the fundamental principles that govern the cosmos. Venturing into the heart of a black hole is a journey that would represent an unimaginable departure from everything we know about space travel. Today's spacecraft, designed to explore the stars and planets of our observable universe, operate within the well-established laws of physics. Yet a black hole is not bound by these laws. Instead, it introduces an entirely different realm, one where time and space behave in ways that defy our expectations. At the core of every black hole lies its most defining feature, the event horizon. This boundary marks the point beyond which nothing, no matter, no light, not even information, can escape the black hole's gravitational grip. As one approaches this boundary, the effects on space and time become increasingly distorted. According to Einstein's theory of general relativity, time slows down in strong gravitational fields. For an observer inside a spacecraft, time outside the black hole would appear to progress at an entirely different rate. This discrepancy could stretch seconds into what feels like years, creating a dizzying experience as the laws of physics break down. Once the event horizon is crossed, the black hole's grip becomes absolute. Traditional physics suggests that the gravitational forces become so intense that no signal, not even light, can escape to the outside universe. Thus, any journey into a black hole would inevitably lead to a one-way trip, with no possibility of return. The fate of any object that crosses this boundary is uncertain. Most likely, it would be pulled toward the singularity, a point where matter is thought to collapse into an infinitely dense state, and the laws of physics cease to function in any meaningful way. While this idea may fuel the imagination, the reality of such a journey remains beyond the reach of current science. In many ways, traveling into a black hole is less an expedition of discovery and more a confrontation with the unknowable. In recent years, however, the field of black hole research has experienced groundbreaking advancements, particularly through the detection of gravitational waves. This new frontier of astronomy, sparked by the LIGO Observatory's groundbreaking discovery in 2015, has opened up an entirely new way to study black holes. Gravitational waves are ripples in spacetime caused by the collision and merger of black holes. Unlike traditional electromagnetic observations, which can be obscured by cosmic dust and gas, gravitational waves offer a direct and unobstructed view into the dynamics of black holes. Since the first detection, numerous black hole mergers have been observed, shedding light on the properties of these invisible giants. These observations are significant for several reasons. Not only do they provide a new method of studying black holes, but they also offer insights into their mass, spin, and frequency of occurrence. These discoveries are reshaping our understanding of the universe, offering profound new perspectives on the nature of gravity, the evolution of cosmic structures, and the fundamental mechanics of the cosmos itself. Thus, the journey into the study of black holes is not just about understanding these peculiar objects. It is about pushing the boundaries of human knowledge and exploring the very fabric of reality itself. Each new breakthrough, whether it's in the form of new black hole classifications or the detection of gravitational waves, adds to our growing understanding of the universe. And as we continue to explore these dark corners of space, we draw ever closer to uncovering the deepest mysteries of existence itself. The ongoing exploration of black holes presents one of the most intriguing and challenging frontiers in modern science. These enigmatic cosmic objects, once considered purely theoretical, have now moved to the center of astronomical research, pushing the boundaries of what we know about the universe. As we discover more about black holes of various masses, particularly those that are unexpectedly large, we are forced to reconsider many aspects of astrophysical theory. These discoveries are raising new questions about how black holes form, how they evolve, and the fundamental nature of the forces at play in their creation. Scientists are particularly fascinated by the origins of these giant black holes. One pressing question is whether these massive black holes are relics of the earliest stars in the universe, or whether their formation is the result of more complex mechanisms, such as the merger of smaller black holes or the collapse of supermassive gas clouds. Understanding this could have profound implications not only for our knowledge of black holes, but for the entire field of cosmology. It could help us better understand the processes that shape the universe from its earliest days, influencing the way galaxies and structures within them came to be. Moreover, the rapid advancements in technology, along with the establishment of networks of gravitational wave observatories, are opening new doors in the study of black holes. These sophisticated instruments allow scientists to detect minute ripples in space-time, offering a fresh way to observe black holes and their interactions with their environments. In the near future, this collaborative, global effort could unveil even more discoveries, shedding light on the behavior of black holes, how they merge, and how they affect the galaxies that harbor them. The data from these observatories will likely allow us to investigate how black holes interact with surrounding matter, possibly offering insight into their role in the formation of stars and the evolution of galaxies. These findings, while impressive, are only the beginning. The study of black holes touches on some of the most profound questions in physics, pushing the boundaries of what we understand about the laws of nature. Black holes force us to confront the limits of our knowledge of space, time, and gravity. At their very core, black holes are regions of space where gravity is so intense that not even light can escape once it crosses the so-called event horizon, the point of no return. This extraordinary characteristic of black holes challenges our understanding of fundamental physics, especially in terms of gravity, space-time, and the behavior of matter under extreme conditions. One of the most intriguing challenges posed by black holes is the apparent contradiction between two of the most successful theories in physics, quantum mechanics and general relativity. General relativity, Albert Einstein's theory, describes gravity as the warping of space-time by massive objects. According to this framework, black holes form when massive stars collapse under their own gravity. On the other hand, quantum mechanics governs the behavior of the smallest particles, such as electrons and photons, operating under entirely different principles. The attempt to reconcile these two theories has led to paradoxes, one of which is the so-called information paradox. The information paradox centers on the question of what happens to the information about matter that falls into a black hole. According to the laws of quantum mechanics, information cannot be destroyed, but black holes seem to violate this principle. Once something crosses the event horizon, it appears to be lost forever. This has led to intense debate within the scientific community, as resolving this paradox could lead to a deeper understanding of both quantum mechanics and general relativity. Black holes also have profound implications for our understanding of time. As an object gets closer to a black hole, time itself slows down relative to an outside observer. This phenomenon, known as time dilation, is a direct consequence of the intense gravitational forces near a black hole. Time dilation raises fascinating questions about causality and the nature of time itself. If time behaves differently near black holes, then observers in different parts of the universe may experience time in vastly different ways. This challenges our conventional notions of temporal continuity and suggests that the very fabric of time is more malleable than we once thought. Despite their mysterious nature, black holes provide a unique window into the evolution of galaxies and the universe at large. The supermassive black holes that reside in the centers of most galaxies play a pivotal role in shaping the dynamics of their host galaxies. These black holes influence star formation, the movement of stars, and the distribution of matter within the galaxy. In this way, black holes act as cosmic engines, helping to drive the processes that form galaxies, stars, and other large-scale structures in the universe. They are not only destroyers, but also creators, playing a central role in the ongoing evolution of the cosmos. As our understanding of black holes deepens, we are moving closer to answering some of the most profound questions in physics and cosmology. Every new discovery pushes the frontier of knowledge further, offering new insights into the workings of the universe. Black holes are not just mysterious objects, but key players in the grand cosmic drama. By studying them, we are uncovering the hidden mechanisms that govern the universe, revealing a reality far more complex and intricate than we could have imagined. The journey to understand black holes is, in many ways, a journey to understand the very nature of existence itself. Throughout the history of our universe, certain cosmic events have emerged as particularly significant due to their immense power and the potential dangers they pose to Earth. These events, often occurring far beyond our solar system, have the capacity to impact life on Earth in ways that are both awe-inspiring and terrifying. Among these celestial phenomena, a few rank highly for their destructive potential, their capacity to alter our planet's environment, and their role in shaping our understanding of the cosmos. One such phenomenon is the supernova. This dramatic event occurs when a star reaches the end of its life cycle and undergoes a catastrophic explosion. The resulting explosion can briefly outshine entire galaxies, releasing an extraordinary amount of energy in the process. If a supernova were to occur within 50 light-years of Earth, the consequences could be dire. The intense radiation emitted by the explosion could shower Earth, harming our atmosphere and potentially depleting the ozone layer. This would increase radiation exposure to living organisms on the planet, making life more vulnerable to the harmful effects of ultraviolet radiation. Although supernovae are rare events, their sheer scale and potential for disruption make them one of the most hazardous cosmic occurrences we can imagine. Another source of concern comes in the form of gamma-ray bursts, GRBs. These powerful explosions are among the most energetic phenomena in the universe and can be triggered by a variety of cosmic events, such as the collapse of massive stars or the collision of neutron stars. A gamma-ray burst directed toward Earth would release an immense amount of radiation, potentially stripping away the atmosphere and damaging the ozone layer. This would expose life on Earth to higher levels of harmful ultraviolet radiation, severely disrupting the ecological balance of the planet. Fortunately, GRBs are incredibly rare, and the vast distances between Earth and their potential sources significantly reduce the likelihood that we will ever experience one. However, the possibility remains, and scientists continue to monitor distant galaxies in search of any signs that a GRB might be directed toward us. Solar flares, though originating much closer to home, present a more immediate and ongoing threat to Earth. These energetic bursts of radiation from the sun can send coronal mass ejections, CMEs, towards our planet. While Earth's magnetic field offers substantial protection from the charged particles emitted during a solar flare, a particularly strong storm could overwhelm this natural defense. The consequences could be catastrophic for technology-dependent societies. Satellites could be disabled, communication systems disrupted, and power grids knocked out, causing widespread chaos. These events, while relatively frequent, are often manageable, but their potential for disruption makes them a cause for concern as technology continues to play an ever larger role in our daily lives. The threat of asteroid and comet impacts has also been a concern throughout history. The most famous example of this is the asteroid believed to have caused the extinction of the dinosaurs. When an asteroid or comet collides with Earth, the energy released can be equivalent to billions of tons of TNT, causing widespread devastation. The impact could trigger climate shifts, tsunamis, and wildfires, leading to massive extinctions. Although the likelihood of such an event happening in the near future is relatively low, the risk remains ever present. Continuous monitoring of near-Earth objects, NEOs, is essential to understanding and mitigating this ongoing threat. International collaboration and planetary defense efforts are crucial in ensuring that we remain prepared for any potential impacts, no matter how distant or unlikely they may seem. Gamma-ray bursts, in particular, offer a unique window into the extreme phenomena of the universe. These bursts, which last anywhere from a few milliseconds to several minutes, release more energy in their brief duration than our sun will produce over its entire lifetime, an expected span of around 10 billion years. This astonishing amount of energy is released during the death throes of massive stars or the violent merging of neutron stars. When a GRB is directed toward Earth, the radiation can have catastrophic effects on the planet, with the potential to strip away the ozone layer and leave Earth vulnerable to harmful ultraviolet rays. Interestingly, GRBs are not merely destructive events. They also offer valuable insights into the nature of the universe. By studying these bursts, astronomers can gain a better understanding of the life cycles of stars and the processes that shape the cosmos. The study of gamma-ray bursts has even helped researchers learn more about the early universe, shedding light on the formation of galaxies and the distribution of matter in space. Despite their potential for devastation, these bursts serve as a source of fascination, providing scientists with the opportunity to explore the extremes of physical laws and test our understanding of the universe's fundamental workings. Neutron stars, the remnants of massive stars that have exhausted their nuclear fuel, occupy a fascinating and mysterious position in the cosmos. These dense objects form when a star collapses under the weight of its own gravity, causing its core to compress to the point where protons and electrons combine to form neutrons. The result is an incredibly dense object, so much so that a single cubic centimeter of neutron star material would weigh as much as a mountain here on Earth. Neutron stars provide a natural laboratory for testing our understanding of physics, particularly under the extreme conditions found nowhere else in the universe. One of the most remarkable features of neutron stars is their ability to warp the fabric of space-time due to their immense gravitational fields. This warping causes observable phenomena, such as gravitational waves, which are ripples in space-time caused by massive objects accelerating through space. When two neutron stars spiral toward each other and eventually merge, they release energy in the form of gravitational waves and also produce heavy elements like gold and platinum in the process. These events, detectable by advanced observatories, not only offer a glimpse into the fundamental processes that govern the universe, but also link the origins of some of Earth's most precious materials to the violent and awe-inspiring events taking place in distant galaxies. In the vast and mysterious expanse of the universe, these cosmic events serve as both a reminder of the potential dangers that lie beyond our planet and a source of wonder, curiosity, and discovery. From the explosive death of stars to the fusion of neutron stars, the universe continues to reveal its secrets, pushing the boundaries of what we know about the cosmos and our place within it. As we learn more about these extreme phenomena, we gain deeper insights into the forces that shape not only our planet, but the very fabric of space-time itself. The ongoing exploration of these events not only enhances our understanding of the universe, but also emphasizes the delicate balance between danger and discovery that exists in the cosmos. Neutron stars are some of the most captivating objects in the universe, but they also come with significant dangers, particularly when we consider their incredibly powerful magnetic fields. These fields can be billions of times stronger than Earth's, making neutron stars, especially magnetars, one type of neutron star, extraordinarily dangerous. Magnetars can unleash intense bursts of radiation, creating perilous conditions for any nearby celestial bodies or spacecraft. Their gamma-ray bursts are so immense that if a magnetar were positioned just a few thousand light years away from Earth, it could threaten the stability of our atmosphere and endanger all forms of life. The energy released in these bursts could be enough to disrupt the delicate balance of life, making these objects both awe-inspiring and terrifying. The mysteries that surround neutron stars have long captivated scientists, pushing the boundaries of our understanding of matter, energy, and the fundamental forces that govern the universe. Researchers relentlessly strive to unravel the secrets of these extreme objects using advanced observational tools and cutting-edge technologies. Their work continues to deepen our knowledge of the cosmos while reminding us of the potential hazards these stars embody. As we study neutron stars, we are not only delving into the fabric of reality, but also acknowledging the profound impact they have on the structure and evolution of the universe itself. One of the lesser-known threats to the stability of solar systems comes from rogue planets, celestial bodies that drift through the galaxy without being tethered to any particular star. These wandering planets can present severe risks to the stability of solar systems they encounter. Imagine a planet that has broken free from its solar system, moving aimlessly through the void of space. When such a rogue planet comes into close proximity to an established solar system, it can wreak havoc on the finely tuned orbits of the planets that call that system home. The gravitational influence of a rogue planet can be so powerful that it can dramatically alter the orbits of nearby planets, causing some to spiral into more eccentric, elongated paths, or even eject them entirely from their solar systems. This disruption can trigger chaos. Planets that once orbited in harmony could be sent into unpredictable orbits, creating the possibility of future collisions. Even moons and asteroids within the system may be at risk as their own trajectories could be altered. However, the gravitational pull of a rogue planet doesn't stop at the planets closest to it. The cascading effects can ripple throughout the entire solar system, shifting the orbits of more distant celestial bodies. A single encounter with a rogue planet could set off a chain reaction that destabilizes an entire system, leading to cosmic upheaval on an unimaginable scale. These types of cosmic disturbances reveal how fragile the balance of our solar system is and underscore the interconnected nature of the universe. The universe is full of forces that can create and destroy, with supernovae and neutron stars playing a key role in the ongoing evolution of galaxies, stars, and even life itself. This delicate balance between destruction and creation is one of the most profound aspects of astrophysics. Magnetars, a particularly extreme subset of neutron stars, are among the most powerful and fascinating objects in the universe. These stars are born from the collapse of massive stars in supernova explosions. What remains is a dense, rapidly rotating neutron star with an incredibly powerful magnetic field, over 1,000 trillion times stronger than Earth's. This magnetic field is not merely a passive byproduct of the star's collapse. Instead, it can cause the surface of the star to crack, leading to violent outbursts of radiation, including X-rays and gamma rays. These eruptions are so intense that they can be detected billions of light years away. The energy released in a single burst can be equivalent to the detonation of several million atomic bombs. Magnetars are among the most energetic objects known to science, and their explosive nature makes them one of the most dangerous phenomena in the cosmos. The potential threat posed by magnetars goes far beyond their immediate vicinity. If a magnetar were located just a few thousand light years away from Earth, the radiation emitted by its outbursts could strip away our planet's atmosphere, making Earth uninhabitable. The study of magnetars, therefore, is crucial not only for understanding the extreme physics of neutron stars, but also for evaluating the potential risks they pose to our planet. Their rarity, the sheer power of their magnetic fields, and their violent outbursts place them at the forefront of astrophysical research. Each magnetar provides scientists with valuable insights into the behavior of matter in conditions that cannot be replicated here on Earth. Another intriguing aspect of cosmic evolution is the phenomenon known as cosmic cannibalism. This occurs when one galaxy merges with or absorbs another, leading to dramatic changes in their structure and dynamics. Galaxies were once thought to evolve in relative isolation, with slow and steady changes occurring over vast stretches of time. However, the realization that galaxies frequently engage in these violent mergers has rewritten that narrative. When galaxies collide, their gas, dust, and stars intermingle, igniting a flurry of new star formation. This disruptive process doesn't just modify the host galaxy, it can completely transform its structure, creating entirely new types of galaxies, such as elliptical galaxies. Understanding these galactic mergers provides a fresh perspective on the nature of galactic evolution. Instead of being a slow and orderly process, it appears to be a chaotic and interconnected web of interactions, where galaxies cannibalize one another, sparking bursts of new star formation that fuel future generations of stars. These interactions play a critical role in the life cycle of galaxies, showing that the universe is constantly in a state of flux and transformation. Through cosmic cannibalism, galaxies are not just evolving in isolation, they are actively shaping one another, contributing to the dynamic and interconnected nature of the universe itself. Each act of galactic cannibalism offers valuable lessons about the way galaxies evolve and the forces that drive their development. From these violent cosmic collisions, new stars are born and new galaxies emerge. This process is integral to the larger picture of cosmic evolution, where destruction leads to creation, and the universe continually reshapes itself in unpredictable and often awe-inspiring ways. The interdependent nature of cosmic forces ensures that the universe remains a place of constant change, where new galaxies, stars, and even the very conditions necessary for life can arise from the ashes of their predecessors. The concept of cosmic cannibalism stands as one of the most thought-provoking phenomena in modern astrophysics, challenging our understanding of the universe's most elusive and mysterious components, such as dark matter. Within the vast expanse of space, galaxies, including our own Milky Way, are not solitary islands. Rather, they reside within enormous halos of dark matter, a substance that remains invisible but exerts a powerful gravitational influence. When two galaxies collide, the interaction of these dark matter halos results in a fusion, creating a greater overall mass. This increase in mass has a profound effect on the gravitational behavior within the newly formed galaxy, dramatically influencing its structure. As these cosmic giants merge, the dark matter halos they carry with them can disrupt the galaxy's dynamics, leading to unusual and chaotic motions among the stars and gas. These irregular movements add layers of complexity to the already enigmatic nature of dark matter. It is through these galactic cannibal encounters that scientists are beginning to reconsider the very framework of galactic evolution. Instead of the slow, linear progression that once seemed to define the life cycle of galaxies, the universe unveils itself as a stage for high-stakes, dramatic interactions and mergers. These events redefine our understanding of how civilizations and celestial bodies evolve within the cosmic theater. Thus, recognizing the role of cosmic cannibalism compels us to rethink not just the development of galaxies, but the entire structure and evolution of the universe itself. These galactic collisions, where one galaxy consumes another, are not mere curiosities. They are pivotal moments in the ongoing saga of the cosmos. One of the most groundbreaking discoveries in cosmology and a key to unlocking the universe's early mysteries is the cosmic microwave background radiation. CMB. This faint but persistent afterglow of the Big Bang serves as an invaluable snapshot of the universe shortly after its inception. Discovered in 1965, the CMB represents a faint radiation that fills the entire universe, detectable as microwaves with a temperature of about 2.7 degrees Kelvin, just above absolute zero. It is a relic from a time approximately 380,000 years after the Big Bang, offering us a unique look at the state of the universe in its infancy. The CMB holds profound significance because it provides us with crucial insights into the conditions that existed in the early universe. By analyzing the minute fluctuations in temperature and density present in this radiation, scientists can make inferences about the universe's primordial structure. These tiny variations are the seeds from which galaxies would later form, set into motion by gravitational interactions. The CMB enables researchers to trace the complex processes by which matter clumped together to create the diverse cosmic structures that we observe today, from galaxies to clusters of galaxies. Moreover, the discovery of the cosmic microwave background radiation provides compelling evidence for the Big Bang theory itself. Prior to its detection, the existence of such radiation had been predicted based on the conditions of the early universe, and its discovery confirmed the model in a way that no other evidence could. The CMB acts as a time capsule, preserving the imprint of a universe that was once incredibly hot and dense. It offers us an unparalleled glimpse into the moments that set the course for the evolution of everything we now see in the cosmos. But the significance of the CMB doesn't stop there. It also serves as a powerful tool for measuring the universe's fundamental parameters. By studying the radiation, scientists can estimate the age of the universe and determine its rate of expansion. As technology advances, researchers are now using more sophisticated telescopes to study this radiation, delving deeper into understanding the universe's origins. This ongoing investigation is not only enriching our knowledge of the universe's early stages, but also unlocking secrets about the darker, more mysterious components of the cosmos, such as dark energy and dark matter. These components, which together account for the vast majority of the universe's mass energy content, are slowly revealing their secrets as we continue to peel back the layers of the cosmic story, piece by piece. One of the most fascinating theoretical concepts that arose from the study of the early universe is that of cosmic strings. These are hypothetical one-dimensional defects in the fabric of space-time, thought to have formed in the moments following the Big Bang. If they exist, cosmic strings could provide valuable insights into the conditions of the universe shortly after its birth. These strings are thought to have formed as the universe cooled, undergoing phase transitions similar to how water turns into ice. The existence of cosmic strings could reveal crucial details about the universe's earliest moments, including the dynamics of the phase transitions that may have shaped its structure. Perhaps the most intriguing aspect of cosmic strings is their potential effect on the gravitational field. Due to their incredibly high mass density, cosmic strings would have the ability to warp spacetime significantly. This warping would create observable gravitational lensing effects, where light from distant cosmic objects is bent around the strings, much like a magnifying lens. Such effects would allow scientists to map the distribution of cosmic strings across vast stretches of space, providing a unique way of observing how these hypothetical structures are scattered throughout the universe. In many ways, cosmic strings act as a kind of scaffolding in the universe, helping to structure the cosmos on the grandest scales. If they exist, these cosmic threads could help us better understand the fundamental architecture of the universe itself and how it has evolved over billions of years. Their study offers a tantalizing glimpse into the forces that shaped the very nature of reality. And as we continue to explore these cosmic mysteries, the true story of the universe slowly reveals itself, one that is far more complex, dynamic, and interconnected than we ever imagined. Cosmic strings, long speculated to be among the universe's most enigmatic phenomena, are thought to generate gravitational waves, ripples in the fabric of spacetime itself. These waves, often produced by cataclysmic cosmic events, have the potential to offer a window into hidden mechanisms of the universe's formation. Gravitational wave observatories, which are continually evolving in both their precision and sensitivity, are on the brink of detecting these subtle tremors. If they succeed, it could provide compelling evidence of the existence of cosmic strings, fundamentally altering our understanding of the universe's large-scale structure. The study of these cosmic threads could reveal not only the conditions that gave rise to the universe's current form, but also the dramatic events that shaped its evolution. Through ongoing advancements in technology, scientists hope to capture these elusive gravitational waves, offering a deeper glimpse into the very building blocks of reality. By exploring the properties of cosmic strings, such as their behavior and interactions, researchers may uncover answers to some of the universe's most profound mysteries. These discoveries could shed light on the nature of dark matter and dark energy, two elusive forces that dominate the cosmos yet remain largely beyond our comprehension. The quest to understand cosmic strings is more than just a search for theoretical knowledge. It is part of a broader endeavor to piece together the cosmic puzzle. This journey seeks not only to explain the universe as it exists today, but also to illuminate the complex history of its formation, from the Big Bang to the present moment. By understanding how the universe has evolved, scientists are also laying the groundwork for uncovering the principles that govern existence itself. Meanwhile, the multiverse theory offers a radically different perspective on our place in the cosmos. According to this hypothesis, our universe is just one of many, possibly an infinite number, existing concurrently within a boundless multiverse. These universes may operate under entirely different physical laws, constants, and dimensions, and some may even bear striking resemblances to our own, while others could be so radically different that they defy all comprehension. One of the more unsettling implications of the multiverse theory is the possibility that in some of these universes, different choices have led to entirely alternate realities. This could mean the existence of versions of ourselves, each living out a distinct life based on different decisions, circumstances, and events. Such a prospect raises profound questions about free will and determinism. If an infinite number of possibilities are realized somewhere in the multiverse, do we truly have control over our actions and outcomes, or are we merely following a preordained path? The very thought of an alternate version of ourselves making different choices, perhaps at a pivotal moment in our lives, can be both captivating and disconcerting. What would life look like if you had made a different decision, taken a different turn? This kind of speculation invites us to reconsider the nature of choice and destiny, nudging the boundaries of what we believe to be possible. Further complicating our understanding is the notion that the universe we inhabit might not be unique or singular in its existence. If the multiverse is real, then our universe is merely one possibility among countless others. This realization can evoke feelings of insignificance, as the vastness of the multiverse suggests that every conceivable scenario, every possible reality exists somewhere, somehow. In this context, our lives and choices may seem like nothing more than fleeting instances in an endless sea of possibilities, raising questions about the meaning and purpose of existence. Despite the speculative nature of the multiverse theory, it has captured the imagination of both physicists and philosophers alike. As the theory gains traction, discussions surrounding it delve into the nature of reality, the essence of life, and the fundamental principles of existence. While testing the multiverse theory remains a daunting challenge, given its far-reaching implications, it continues to provoke deep reflection and intrigue. Equally captivating is the concept of time travel, particularly through theoretical passages known as wormholes. These hypothetical shortcuts through space-time were first proposed by physicists Albert Einstein and Nathan Rosen, who envisioned them as bridges linking distant regions of the universe. The idea of traveling through a wormhole has profound implications for our understanding of both general relativity and quantum mechanics, opening the door to the possibility of time travel. However, the idea of moving through time via wormholes presents significant challenges, especially when it comes to the concept of causality. If time travel were possible, it could lead to paradoxes that defy our conventional understanding of cause and effect. One of the most famous examples is the grandfather paradox, in which a time traveler could prevent their own existence by altering events in the past. Such paradoxes raise deep questions about the linearity of time. Is time a straight progression of events, or is it a more intricate and multifaceted web of possibilities? These paradoxes challenge our current understanding of reality and force us to reconsider our most basic assumptions about the flow of time. If time travel were to become a reality, it might not only revolutionize our understanding of physics, but also reshape our perception of our place in the universe in relation to both past and future. As the fields of cosmology, quantum mechanics, and general relativity continue to advance, our understanding of these fundamental concepts grows ever more intricate and profound, whether through the exploration of cosmic strings, the contemplation of the multiverse, or the dream of time travel. These theories invite us to push the boundaries of what we know and to challenge the very fabric of reality itself. The pursuit of these mysteries may one day reveal answers to some of the universe's most enduring questions, offering insights that could change the course of human understanding for generations to come. The stability of wormholes is a critical area of study that continues to intrigue both physicists and theorists alike. To keep a wormhole open so that it could theoretically be used for travel, a concept has emerged suggesting that exotic matter with negative energy density is required. However, this type of matter has yet to be observed in the natural world. The absence of such matter challenges our current understanding, leaving scientists to speculate about its existence and its role within the broader structure of the universe. Our current framework of physics does not offer an entirely coherent means to support the practicality of constructing or even navigating through such extraordinary structures. As researchers dive deeper into the complexities of time travel via wormholes, they are forced to reconcile these daring theories with the more established laws of physics. This interaction between the accepted principles of physics and the speculative possibilities of time and space has become a rich and exciting field of study. The exploration of wormholes, therefore, not only broadens our understanding of the cosmos, but also pushes the boundaries of what we consider to be possible, testing the very foundations of our scientific knowledge. At the same time, the simulation hypothesis has sparked a profound shift in how we think about the nature of reality. This theory suggests that our perception of the physical world around us is nothing more than a sophisticated simulation, an artificial construct far more complex than anything seen in popular science fiction. If this hypothesis holds any truth, it raises deep philosophical questions about the very essence of our existence. Are we merely characters within an immense, intricately programmed world, completely unaware of the artificial nature of our surroundings? What would it mean for our understanding of life if we were indeed living in a simulation created by some higher intelligence or an advanced technological system? The implications of this hypothesis stretch far beyond mere speculation. One significant challenge lies in how we define consciousness. If our thoughts, emotions, and experiences are generated by an extremely advanced system, it begs the question, what is the true nature of self-awareness? How do we redefine sentience when the mind itself might be a product of an elaborate digital environment? Such a perspective forces us to reconsider traditional views of consciousness, suggesting that our understanding may be confined to the limits set by the entities who created the simulation. Furthermore, the ethical implications of a simulated existence present a compelling challenge. Who, then, is in control of this reality, and what moral obligations do they hold towards us? If we are indeed living in a simulation, the very concepts of morality and free will may need to be rethought. In a world where reality can be altered at will by the creators of the simulation, can we still distinguish right from wrong? Can we truly make free choices if our entire existence is being shaped by external forces? These questions not only have the potential to redefine ethics, but also point to a future where our understanding of what it means to be human may be forever altered. Moreover, the simulation hypothesis stirs curiosity about the trajectory of technology and its role in the future of humanity. If it is possible to create simulations so indistinguishable from reality, we must consider the profound consequences such advancements could have on human knowledge, scientific discovery, and even our perceptions of life itself. Our current understanding of reality, so firmly rooted in the physical world, might one day need to evolve to account for a reality where the line between the simulated and the real is increasingly difficult to draw. In a similar vein, quantum entanglement presents a challenge to classical physics that seems almost surreal. This phenomenon occurs when two or more particles become entangled, such that the state of one particle is instantly connected to the state of another, regardless of the vast distance between them. This instantaneous connection seems to defy the classical understanding of locality, which states that objects can only be influenced by their immediate surroundings. As scientists investigate quantum entanglement more deeply, they are forced to reconsider how we define space, time, and causality. Under the influence of entanglement, the assumption that interactions only happen locally begins to dissolve. This quantum reality suggests that information may be transmitted instantaneously across vast expanses of space, seemingly breaking the established rules of relativity, which asserts that nothing can travel faster than the speed of light. The implications of this discovery are monumental. If information can travel faster than light, our understanding of the fundamental nature of the universe must undergo a radical transformation. These revelations continue to excite physicists who are beginning to explore whether the very fabric of the universe is interconnected in ways we cannot yet fully comprehend. Furthermore, quantum entanglement raises deeper philosophical questions about the independence of objects in the universe. Are particles truly separate entities, or are they merely different manifestations of a larger interconnected reality? Such questions challenge the core assumptions of physics and push us toward reconsidering whether the universe is fundamentally discrete, composed of isolated particles, or whether it is continuous, a fluid and interconnected whole. As our understanding evolves, quantum entanglement may inspire not only modifications to established theories, but also the development of entirely new frameworks for understanding the universe. This leap into the quantum realm has the potential to revolutionize numerous technologies. In fields like computing and communication, quantum entanglement could lead to advancements once thought impossible, such as ultra-secure communication channels and unimaginable increases in computational power. As we venture further into this uncharted territory, quantum mechanics promises to reshape our understanding of reality and challenge the very foundation of traditional physics. The theory of cyclic universes offers another radical rethinking of time and existence. If the universe is caught in an endless cycle of birth, evolution, and destruction, it forces us to reconsider our basic notions of reality. Is time truly linear, as we often experience it, or is it cyclical, with each cycle bringing about the repetition of events? In such a model, the universe may collapse and re-expand infinitely, meaning that everything we know, every life, every planet, every star, may have already existed countless times before. If the universe repeats itself endlessly, what does this mean for the concept of individuality and uniqueness? The idea that our lives might be but fleeting moments in an eternal cycle raises unsettling questions. If everything we experience will come back again in some form, what does that suggest about our significance in the grand scheme of existence? Are we truly unique, or is everything merely a repetition of a cosmic loop beyond our control? The concept of a cyclic universe forces us to confront the possibility that the very notion of time and the meaning of our lives could be radically different from what we have long believed. Each of these theories, wormholes, the simulation hypothesis, quantum entanglement, and cyclic universes, challenges our understanding of reality, pushing the limits of physics and metaphysics. As we continue to explore these phenomena, we are forced to confront the possibility that the universe is far more mysterious and interconnected than we can yet fathom. And as we journey deeper into these uncharted territories, we may ultimately find that the answers to the most profound questions about existence lie far beyond our current comprehension. The cyclic universe theory opens the door to a cascade of profound existential questions, delving into the very fabric of fate and destiny. If the universe operates in an eternal cycle with recurring phases of creation, destruction, and rebirth, it begs the question, does this mean that our actions are predestined, mere echoes of a grand, unchangeable plan? If the cycle repeats infinitely, are we simply reliving the same events over and over with only slight deviations? These chilling yet fascinating questions urge us to reconsider what we know about free will, choice, and the nature of time itself. At the heart of this theory lies the unsettling possibility that the universe is a grand performance in which we are not active participants, but rather actors bound to follow a script written eons ago. Yet, within this cyclical pattern, can we still claim agency? Are we truly free to make decisions? Or are we merely playing out our roles within an unbreakable, eternal recurrence? The implications of this are staggering, as it challenges the very essence of human existence. If the universe is bound by a predestined pattern, are our lives meaningful, or are they just part of an unceasing loop, forever doomed to repeat? Such reflections challenge us to rethink our understanding of existence. The notion of a predetermined universe forces us to confront uncomfortable truths about our place in the cosmos. Each new revelation only deepens the mystery, highlighting how little we truly understand about the intricate design that may govern everything around us. In this sense, the cyclic universe theory becomes not just a scientific hypothesis, but a philosophical mirror, forcing us to examine the very nature of reality. Meanwhile, the idea of parallel universes captivates scientists and thinkers alike, offering a tantalizing glimpse into the very fabric of reality. Imagine, our universe, vast and intricate as it is, may be just one of countless others, each governed by different physical laws or unfolding under alternative historical circumstances. This concept, which straddles the realms of quantum mechanics and string theory, introduces the possibility of infinite variations of existence, where alternate versions of ourselves might live out different fates. The thought of these alternate realities offers fertile ground for the imagination, sparking thought experiments that test the limits of what we believe to be possible. Yet, with this thrilling possibility comes a profound sense of trepidation. The multiverse theory is not just a mind-bending intellectual exercise. It challenges the very foundations of what we know to be true. If infinite universes exist, each with different outcomes, it raises unsettling questions about the role we play in our own reality. If every possible version of events happens somewhere, what does that mean for the choices we make in our own universe? This uncertainty can be deeply unsettling, shaking the confidence we place in our own significance and place in the cosmos. It pushes against the boundaries of coherence that many scientists rely on in their quest to make sense of the universe. Even more perplexing is the fact that while the multiverse theory is mathematically intriguing, it remains largely unprovable. The absence of direct empirical evidence makes it a topic that many in the scientific community approach with caution. The scientific method, which hinges on the ability to collect and analyze tangible data, cannot yet offer the means to test or validate the existence of parallel universes. As a result, the multiverse remains a speculative theory, one that many scientists view with skepticism. Without concrete evidence, the idea of parallel universes risks remaining a tantalizing yet elusive possibility, pushing the boundaries of both physics and philosophical inquiry. As technology continues to advance, however, the search for evidence of alternate realities persists. The interplay between excitement and anxiety around the concept of parallel universes is a reflection of the dual nature of scientific inquiry. The pursuit of knowledge drives us to confront uncomfortable truths, forcing us to grapple with the limits of our understanding, as well as the potential for discovery in uncharted territories. Antimatter, one of the most intriguing and perplexing phenomena in the universe, adds yet another layer of complexity to our understanding of reality. It exists as the mirror image of ordinary matter, with every particle of regular matter having a corresponding antiparticle, possessing the same mass but the opposite charge. When matter and antimatter come into contact, they annihilate each other in a burst of energy, a process that releases vast amounts of power. This fundamental characteristic has made antimatter both a source of fascination and concern for scientists, as its destructive potential is immense. The idea of harnessing antimatter for energy or weaponry presents both exciting possibilities and grave dangers. A single gram of antimatter could release the same energy as roughly 24,000 tons of TNT, a staggering amount of destructive force. This overwhelming energy density raises serious ethical and safety concerns, particularly when considering the catastrophic consequences of a miscalculation or accident involving antimatter. The potential for disaster, whether in a scientific laboratory or on a global scale, makes the study of antimatter both a thrilling and terrifying endeavor. The challenges associated with antimatter are also technical in nature. Producing antimatter is an extraordinarily labor-intensive and costly process, requiring vast amounts of energy to create even the tiniest amounts. At present, the most advanced facilities can generate only minute quantities, each of which comes with an astronomical price tag. The idea of using antimatter for practical applications, such as energy production or propulsion, seems almost unattainable given the current limitations of technology. Moreover, containing antimatter presents an additional challenge. Because it cannot exist in contact with normal matter, it must be stored in a vacuum, isolated by powerful magnetic and electric fields. Achieving this level of control requires an unprecedented degree of precision and engineering expertise, making the prospect of utilizing antimatter in a meaningful way seem increasingly unlikely. Despite these enormous challenges, the promise of antimatter continues to capture the imagination of scientists and the public alike. Its potential for revolutionizing energy production, space travel, and even warfare is both inspiring and terrifying. The duality of antimatter, its potential for both creation and destruction, highlights the complex nature of scientific discovery, where awe and fear are often intertwined. As our understanding of antimatter deepens, the need for ethical consideration and responsible research becomes ever more urgent. The pursuit of knowledge must be tempered by a recognition of the potential consequences of our actions. Finally, the Fermi paradox introduces one of the most perplexing questions in modern science. Where are all the extraterrestrial civilizations? Despite the vastness of the universe, with billions of stars and even more potentially habitable planets, we have yet to find any definitive evidence of intelligent alien life. This paradox underscores the contradiction between the high probability of extraterrestrial life existing and the complete lack of contact or observable signs of their existence. One possible explanation for this paradox is the notion that advanced civilizations may pose a threat to humanity. If intelligent life forms are out there, they may possess technologies that far exceed our own, creating the potential for dangerous consequences if we were to make contact. History on Earth shows that encounters between technologically distinct civilizations have often led to conflict, with the less advanced societies typically suffering the most. This raises the possibility that advanced alien civilizations, if they exist, may not be interested in contact or may even actively avoid it, fearing the risks of interacting with a relatively primitive species such as ours. In the face of these vast and unsettling mysteries, we are left to contemplate our place in the universe. Are we alone? And if not, what does that mean for our future as a species? The Fermi paradox, much like the other theories discussed here, forces us to confront the unknown. It challenges our assumptions about existence, life, and the future, and invites us to explore the limits of our understanding in the hope that one day we may find answers to the most profound questions of all. Furthermore, an intriguing hypothesis suggests that advanced civilizations may intentionally avoid contact with us, or possibly even become extinct before achieving the technological capacity to communicate across interstellar distances. This perspective offers a thought-provoking view of the cosmos. While life in the universe may be widespread, intelligent life capable of sustained, meaningful communication could be exceptionally rare. As humanity continues its search for signals or signs of extraterrestrial intelligence, we are faced with an important dilemma. It is no longer just a scientific pursuit, but also a quest fraught with the potential hazards that such contact could bring. The Fermi paradox, which raises the question of why we have not yet encountered any alien civilizations, encourages us to reflect deeply on our own place within the universe. Are we truly isolated, or is there a deliberate silence surrounding us, signaling that the universe may be teeming with intelligent beings who have chosen to remain hidden. This silence compels us to tread carefully, acknowledging that the discovery of intelligent life could come with unknown dangers that might challenge the very fabric of human existence. Therefore, our search for extraterrestrial intelligence is not only a matter of scientific inquiry, but one of profound ethical significance for humanity. In parallel, the enigmatic nature of black holes continues to intrigue and mystify scientists, pushing the boundaries of our understanding of space and time. One of the more tantalizing propositions is the idea that black holes could function as portals or gateways to other universes. According to certain interpretations of the fabric of space-time, the immense gravitational forces within a black hole could create a tunnel, linking our universe to others that may exist beyond our perception. If proven to be true, such a concept would dramatically alter our understanding of reality, offering new perspectives on the structure of the cosmos and our place within it. This revelation could force us to reconsider the very nature of existence itself, raising fundamental questions about the universe's limits and the potential for alternate realities. Another perplexing idea connected to black holes is the information paradox that arises when matter crosses the event horizon. Classical physics asserts that nothing, not even light, can escape from a black hole once it crosses this boundary. However, quantum mechanics maintains that information in the form of particles and energy cannot be destroyed. This conflicting idea has led to an intense scientific debate. What happens to the information of the matter that falls into a black hole? If resolved, this paradox could provide groundbreaking insights into the relationship between gravity and quantum mechanics, potentially paving the way for a unified theory that governs all of physics. Such a discovery would not only deepen our understanding of the cosmos, but could open doors to technological innovations that we cannot yet imagine. Moreover, black holes might hold the key to unlocking exotic forms of matter or energy, further complicating their mystery. Some scientists speculate that if black holes could be harnessed or manipulated, they might offer access to materials or energy sources that do not exist in our observable universe. This could revolutionize technology, making interstellar travel a reality and potentially transforming our capacity to explore the vastness of space. These hypothetical scenarios highlight the profound mysteries that black holes present and pushing the limits of our knowledge and expanding the very scope of scientific exploration. Every new discovery offers a potential redefinition of the fundamental principles of physics, drawing us closer to a more comprehensive understanding of the cosmos. The discovery of a new fundamental particle could have similarly far-reaching implications, reshaping our understanding of the universe in ways that we cannot yet foresee. The current standard model of particle physics describes the building blocks of matter and the forces that govern their interactions. But this model is far from complete. It leaves several critical questions unanswered, particularly regarding the elusive nature of dark matter and dark energy, two phenomena that together constitute most of the universe. Should scientists succeed in uncovering a new particle, it could provide insights into these mysteries, potentially illuminating the properties of dark matter and revealing its role in shaping galaxies and the cosmos as a whole. Such a discovery could not only expand the standard model, but also lead to a deeper understanding of the fundamental forces that govern the universe's origins and its current state. Additionally, the discovery of new particles could point toward the existence of additional dimensions or unknown forces beyond the ones we currently recognize. This would force us to reconsider established scientific principles and explore areas of inquiry that we have yet to venture into. Beyond theoretical implications, the discovery could fuel technological advancements as researchers work to develop new methods for studying the properties of these particles. Such breakthroughs could have practical applications across various fields, including material science, computing, and even medicine. A new particle represents both a puzzle piece and a key to unlocking the universe's deeper secrets, inviting scientists to question long-held assumptions and explore new territories of physics. In parallel to these scientific advancements, humanity must also prepare for potential space-related disasters, which could have catastrophic consequences for our planet. Events such as asteroid impacts or solar storms present real threats, and addressing these risks requires a combination of scientific knowledge, technological innovation, and international collaboration. Astronomers continuously monitor the skies for near-Earth objects that could pose a threat. When a potential hazard is detected, teams of scientists assess its trajectory and determine whether it is on a collision course with our planet. If a threat is identified, several strategies can be employed to mitigate the risk. One approach involves using kinetic impactors, spacecraft designed to deliberately collide with an asteroid, changing its course. Another idea under investigation involves the use of gravitational tractors, spacecraft placed near an asteroid to gradually alter its trajectory using the craft's gravitational pull. Similarly, solar storms, massive bursts of radiation from the sun, can wreak havoc on Earth's infrastructure, disrupting satellites, power grids, and communication systems. To combat this, space weather forecasting has become an essential tool. Agencies like the National Oceanic and Atmospheric Administration, NOAA, and other global space organizations keep a constant watch on solar activity. When significant solar events are predicted, warnings are issued, allowing governments and industries to take precautions, such as safeguarding electronics and adjusting satellite orbits. Addressing potential space-related disasters is a global challenge that requires extensive cooperation, as no single nation can face these threats alone. Working together, countries can share critical information, improve technology, and develop robust response strategies to ensure the safety and security of all. As we prepare for potential space disasters, monitoring celestial objects like asteroids becomes increasingly important. NASA and other space agencies around the world collaborate through initiatives like the Near-Earth Object Observations Program, which uses telescopes to survey the skies for potential threats. When a new asteroid is discovered, it is assigned a designation that helps scientists categorize its size, trajectory, and proximity to Earth. If the asteroid poses a significant risk, various protocols are set in motion to track its path with greater precision. The goal is to determine whether the asteroid presents a viable threat to Earth. If so, discussions about deflection methods, such as kinetic impactors or gravitational tractors, are initiated. Although these strategies remain theoretical for now, they represent critical avenues of research aimed at protecting our planet. In addition to scientific collaboration, educating governments and the public about the importance of preparedness is vital. Comprehensive response plans are developed to manage evacuations or interventions, and partnerships between space agencies foster a unified global response. This ensures that humanity remains proactive in safeguarding itself from the unpredictable forces of space. Finally, astronauts embarking on deep space missions face significant psychological challenges due to isolation and confinement. The stresses of prolonged space travel can lead to anxiety, stress, and a sense of separation from loved ones. To help mitigate these effects, space agencies like NASA employ a variety of strategies. Astronauts undergo intense psychological training before their missions, preparing them for the unique stresses they will face. They are also trained in communication and teamwork, skills essential for maintaining healthy interpersonal relationships when confined in small spaces for extended periods. During missions, astronauts are provided with regular communication with family and friends, as well as scheduled downtime for hobbies and relaxation. This support system plays a crucial role in ensuring the mental well-being of astronauts and maintaining their overall performance during their missions. These preparations reflect the increasing recognition of the psychological toll that deep space missions. In fact, the mental health of crew members is a top priority for mission planners and behavioral health experts. Astronauts are continuously monitored remotely by specialists who are trained to detect signs of stress, anxiety, or mental fatigue, providing critical support when necessary. In addition to this, astronauts participate in regular check-ins with psychological experts to help them process their experiences and maintain a balanced emotional state. This proactive approach reflects a deep understanding that the success of a mission hinges on more than just physical preparedness. It also requires emotional resilience. Such an approach underscores the importance of fostering mental health awareness, even in the most challenging and isolating environments, such as deep space. The need for psychological support is integral to the success of human space exploration and colonization efforts, where isolation and pressure are constants. However, as humanity looks towards the future of space exploration and the possibility of colonizing other planets, it becomes clear that there are numerous ethical concerns that we must confront. These questions are more than just technical or logistical. They force us to consider the broader implications of human expansion into the cosmos. One of the primary ethical dilemmas involves planetary stewardship. As we plan to stretch our reach beyond Earth, we must carefully consider the potential ecological impact of our presence on other celestial bodies. Mars, often seen as a prime candidate for colonization, presents particular ethical challenges. If we were to colonize Mars, what effect would this have on any microbial life that might exist there, even in a dormant or latent state? The possibility of contaminating or disrupting pristine extraterrestrial ecosystems raises important moral questions. Should human expansion take precedence over the preservation of other worlds? This debate has sparked considerable discussion within the scientific community and raises concerns that we must tread lightly as we move forward. Alongside these ecological concerns is the issue of social inequity. The vision of interplanetary colonization brings up important questions about who gets to go and who will remain behind on Earth. It's not difficult to imagine a scenario where only a select few, likely the wealthy or politically influential, would have the privilege of living on a new planet, leaving those who are less fortunate behind to continue facing challenges such as poverty, environmental degradation, and social unrest. In this context, colonization could perpetuate rather than alleviate existing inequalities. The dream of creating a new home for humanity should not become another avenue for deepening societal divides. Rather, it should be an opportunity to promote inclusivity and ensure that all people, regardless of their socioeconomic status, have an equitable chance to participate in humanity's next great leap. This brings us to another fundamental concern: governance and human rights. What kind of political systems will emerge in these new interplanetary societies? On Mars or another distant planet, who will make the rules and how will laws be enforced? The absence of established legal frameworks in these new environments could lead to exploitation or violations of basic rights. In such uncharted territory, power dynamics may easily become skewed, with those in positions of authority potentially infringing upon the freedoms of others. The complexities of governance in space settlements highlight the necessity for thoughtful planning and the establishment of fair and just systems of rule. It's crucial that as we design our future on other planets, we also consider how to create societies that uphold the principles of equity, justice, and human rights. Moreover, the ethical implications of space colonization inevitably prompt a deeper reflection on our responsibilities here on Earth. As we look toward the stars and dream of establishing human settlements on other planets, we must not lose sight of the urgent need to address the crises facing our home planet. Issues such as climate change, resource depletion, and environmental degradation demand our immediate attention. We cannot allow the drive to explore and inhabit other worlds to overshadow the critical work that still needs to be done on Earth. In fact, the desire to spread humanity across the cosmos must be paired with a steadfast commitment to preserving and nurturing the planet that has supported us for millennia. Balancing these dual ambitions to explore the universe while safeguarding our home is an essential aspect of the ethical considerations surrounding space colonization. The push for a multiplanetary future also raises questions about risk and reward. As we venture into the unknown, we are confronted with a complex web of both exhilarating possibilities and potential dangers. Ensuring that our explorations do not compromise the safety of our planet or the well-being of future generations is one of the foremost challenges facing modern space missions. This dual focus on discovery and precaution is integral to the planning and execution of contemporary space missions. Space agencies such as NASA, the European Space Agency, and private companies like SpaceX are acutely aware of the risks involved in space travel. To mitigate these dangers, they have established rigorous safety protocols and procedures, carefully planning each step of every mission. For instance, before launching any spacecraft, extensive simulations are carried out to predict and address potential hazards. These simulations test every facet of a mission, from the mechanics of the spacecraft to the psychological well-being of the crew. Research is also conducted to better understand the challenges posed by long-duration space travel, including radiation exposure and the effects of microgravity on the human body. By taking these preparatory measures, space agencies hope to ensure that space exploration remains as safe as possible while still allowing for the pursuit of knowledge and the expansion of human frontiers. As humanity sets its sights on the vast uncharted territories of the cosmos, we must carefully weigh the potential rewards against the risks. The future of space exploration is fraught with uncertainty, but it is also filled with unprecedented opportunities. Whether we succeed or falter in these endeavors, the journey toward becoming a multiplanetary species will continue to challenge our understanding of what it means to be human, SETI, forcing us to confront not just our technological prowess, but our ethical obligations to one another and to the worlds beyond. International collaboration between countries is essential for the advancement of space exploration. When nations share their knowledge and resources, they ensure not only the safety of astronauts, but also the protection of the very environment we rely on here on Earth. This cooperation sets a framework for improved safety standards, creating safeguards that mitigate the risks of space missions. Such efforts help to prevent incidents that could have catastrophic consequences, not just for the astronauts in space, but for the ecosystems on Earth, which are inherently interconnected with the success of our missions. In addition to the safety concerns, there are also profound ethical considerations that guide space exploration. One of the most pressing is the search for extraterrestrial life. This endeavor, while exciting, raises crucial questions about contamination. As we look for signs of life beyond our planet, scientists must consider the potential risks of introducing Earth-based organisms into alien ecosystems. The introduction of foreign microbes could disrupt delicate extraterrestrial environments, leading to irreversible consequences for the celestial bodies involved. To prevent this, researchers advocate for stringent planetary protection policies. These measures ensure that while we pursue knowledge, we also preserve the integrity of other worlds and prevent human interference from permanently altering them. This delicate balance between exploration and caution is a reflection of the broader responsibility we bear as a species. Scientific progress must always be weighed against the ethical obligation to protect not just our planet, but also the wider cosmos. By prioritizing safety, ethics, and international collaboration, humanity can continue to uncover the mysteries of the universe without compromising the delicate balance that sustains life on Earth. This approach opens the door to a future where the wonders of space exploration can coexist with the wisdom needed to navigate the profound responsibilities it entails. By doing so, we can inspire the next generation to embrace a future of discovery, one that is informed by both awe and careful consideration. The task of predicting cosmic events that could pose a threat to humanity is one of the most complex endeavors facing scientists today. The vast scale of the universe, coupled with its inherent unpredictability, presents numerous obstacles. Celestial events such as asteroid impacts, comet trajectories, or supernovae can occur without warning. While astronomers can track known near-Earth objects with varying degrees of precision, many smaller or less predictable bodies remain undetected. This lack of complete knowledge creates significant uncertainty, making it challenging to accurately assess the potential risks posed by these objects. The challenges become even more daunting when we consider the immense distances and timescales involved in the universe. For instance, a comet may travel for years toward the inner solar system, its path influenced by the gravitational forces of other celestial bodies along the way. As a result, its trajectory is never guaranteed, and changes can happen unexpectedly. The unpredictable nature of these objects means that by the time an asteroid or comet is detected, it could be too late to implement any mitigation strategies. This uncertainty underscores the difficulties scientists face when attempting to forecast cosmic threats. Current technological limitations further complicate matters. While our telescopes and sensors are becoming more advanced, they are far from perfect. Many potentially hazardous objects slip through the cracks, going unnoticed until it's too late. The technology required to monitor space for these objects is still evolving, and unfortunately, funding for these projects is limited. With many competing scientific priorities, securing sufficient investment for space monitoring systems remains a challenge. Scientists are pushing for more advanced early detection systems, but without adequate resources, progress is slow. Communicating these risks to the public is yet another hurdle. The science of predicting cosmic threats is complex and often difficult for the general public to grasp. Misunderstanding or fear can easily spread, especially when the stakes are high. Scientists face the challenge of conveying the potential risks in a way that is both accurate and accessible, avoiding unnecessary panic while ensuring that society is adequately prepared. Thus, fostering an open and honest dialogue about the likelihood and implications of cosmic events is as essential as the scientific work itself. The quest for extraterrestrial life has transformed our approach to space exploration in ways that go beyond simply understanding the universe. This search raises profound questions about the origins of life itself. What are the conditions necessary for life to exist? What factors must align for an environment to support living organisms? As we probe deeper into space, these questions are not just theoretical. Every discovery and technological breakthrough opens the door to new questions and deeper exploration. One of the key insights driving this exploration is the study of extreme environments on Earth. Places like deep-sea hydrothermal vents and highly acidic lakes, where life thrives against all odds, have led scientists to reconsider where life might exist beyond our planet. These environments, often home to organisms known as extremophiles, reveal that life can adapt and flourish in conditions that were once considered inhospitable. This realization has spurred interest in exploring similar environments on other planets and moons, such as the icy surface of Europa or the methane lakes on Titan. By studying these potential habitats, scientists are reshaping their understanding of life's resilience, and the places where it might thrive in the cosmos. Alongside these discoveries, the search for intelligent life, commonly known as SETI, Search for Extraterrestrial Intelligence, has sparked a revolution in technology. SETI efforts use sophisticated instruments and algorithms to detect radio waves or other signals that could indicate the presence of extraterrestrial civilizations. Each breakthrough in this area not only brings us closer to answering the question of whether we are alone in the universe, but also accelerates the development of new technologies. These advances have led to improvements in artificial intelligence and data processing, as the tools we develop to scan the cosmos are applied to other fields as well. The implications of the search for extraterrestrial life are profound. Theories about the origins of life on Earth are deepened by the study of cosmic phenomena and other celestial bodies. By examining how the Earth formed and understanding the processes that led to the creation of our biosphere, scientists gain insights into the conditions that may be necessary for life elsewhere. This interconnected quest for knowledge fuels research across multiple disciplines, including biology, astronomy, and geology. As these scientific boundaries continue to be pushed, we move closer to understanding the mysteries of life in the universe. SETI plays an essential role in understanding not only the potential for intelligent life elsewhere, but also the risks that might arise from such contact. Monitoring and analyzing signals from space provides an opportunity to prepare for the various outcomes that may result from communication with an advanced extraterrestrial civilization. The discovery of a deliberate signal could indicate the existence of a civilization with technology far beyond our own. While the idea of first contact is exciting, it also brings with it significant concerns about safety and security. Not all signals from space may be benign. Some civilizations may have motives or capabilities that are far different from anything we can imagine. Therefore, careful analysis of any signals we receive is crucial to understanding the nature of the civilization sending them and the potential risks involved. Furthermore, SETI's efforts are not solely focused on uncovering the friendly, familiar elements of the cosmos. As our technological capabilities evolve, so too does the complexity of the questions we ask about extraterrestrial life. One such concept gaining traction in the scientific community is the zoo hypothesis, which proposes that advanced alien civilizations might deliberately avoid direct contact with humanity, choosing instead to observe us from a distance. This idea adds another intricate layer to the discussion about the existence of extraterrestrials. If these civilizations exist and are indeed monitoring us, understanding their technologies, social structures, and ways of life could help us prepare for any future interactions, whether these beings are neutral, inquisitive, or even hostile. The importance of SETI, then, is not just about detecting signals, but also about framing the larger conversation about what humanity would do if concrete evidence of alien intelligence were discovered. As our search for extraterrestrial signals becomes more sophisticated, we are faced with the need to carefully consider how we would respond. This consideration spans not just the scientific community, but also touches on philosophical and ethical questions that challenge our fundamental understanding of our place in the universe. What would our obligations be if we discovered intelligent life beyond Earth? Through SETI, we don't just seek alien life, we enter a broader conversation about preparedness and the potential challenges that such a discovery might present. It forces us to consider what lies ahead in an increasingly complex, vast, and largely unexplored cosmos. At the same time, space agencies worldwide have come together in an unprecedented effort to monitor cosmic threats, creating a spirit of international collaboration that transcends political and national boundaries. The primary focus of this cooperation is the detection and tracking of near-Earth objects, NEOs, such as asteroids and comets, which pose a potential risk to our planet. By sharing data from telescopes and satellites, these agencies are able to make more accurate predictions about the trajectories of these objects, thereby enhancing our ability to mitigate potential impacts. A remarkable example of this international cooperation is NASA's Near-Earth Object Program, which works in tandem with the European Space Agency, ESA, the Japan Aerospace Exploration Agency, JAXA, and various research institutions around the globe. Together, they have built a global network of observatories that continuously scan the skies, identifying and cataloging new celestial objects as they emerge. This collaboration is crucial because it not only improves our understanding of cosmic threats, but also enhances our ability to develop strategies for responding to these dangers. Beyond asteroids, space agencies also collaborate on initiatives like the Space Situational Awareness Program, which focuses not only on monitoring NEOs, but also on tracking space debris. This debris poses a significant risk to satellites and spacecraft, threatening the infrastructure that supports our communication, navigation, and security systems. Through shared technology and infrastructure, scientists are able to analyze data with greater accuracy, providing quicker warning systems. In some cases, this collaboration leads to the development of deflection missions, where coordinated efforts aim to alter the trajectory of potentially dangerous objects, preventing catastrophic events. As we continue to explore the cosmos, the significance of these alliances cannot be overstated. The stakes are high. The movement of celestial bodies is governed by intricate forces that demand preparedness and vigilance. By uniting their knowledge and resources, space agencies can work together to ensure that Earth remains protected from cosmic threats, safeguarding future generations, and reinforcing the power of collective scientific endeavor. Through these alliances, humanity can tackle the most pressing challenges of space exploration, drawing on shared knowledge and innovation to protect our planet and its future inhabitants. Public perception plays an indispensable role in the trajectory of space exploration. It has the power to shape funding, influence policymaking, and stir public enthusiasm for missions that push the boundaries of human achievement. When people feel a personal connection to space exploration, they are more likely to advocate for increased investment in science and technology. The iconic moon landing of 1969, for example, was a catalyst for public interest in space and solidified government support for future missions. The excitement surrounding that event created a sense of collective pride, leading to greater funding and the continued development of space technology. However, public sentiment is not always universally positive. There are moments when negative perceptions about the costs and risks associated with space exploration can lead to a decline in support. The perceived dangers of space missions often come under scrutiny, particularly concerns about the safety of astronauts, the environmental impact of rocket launches, and the immense financial costs involved. The tragic loss of the Space Shuttle Challenger in 1986 serves as a poignant reminder of the risks inherent in space exploration. Such events can dramatically affect public opinion, and policymakers often find themselves balancing the potential benefits of space exploration against the heavy emotional and financial costs. Moreover, the portrayal of space missions in media, through documentaries, inspiring films, and news outlets, also has a profound impact on public perception. Well-crafted documentaries and accurate news reporting can foster a sense of wonder and hope about humanity's place in the cosmos. When the narrative shifts to emphasize the tangible benefits of space exploration, such as technological advancements and scientific discoveries that directly benefit life on Earth, it creates a more favorable view of space missions. This shift in perspective is essential for maintaining enthusiasm and support for current and future projects, especially as the world continues to face challenges on Earth that space exploration could help address. Ultimately, as humanity strives to push what is possible in space exploration, public perception acts as both a compass and a shield. It guides the enthusiasm that fuels scientific discovery and technological progress, while also placing limits on the ambitions of space agencies and private companies. Striking a balance between bold exploration and addressing public concerns is crucial for the continued success of space missions, allowing us to venture safely into the unknown. To safely and effectively explore the cosmos, a series of technological advancements must be developed. Among the most essential of these is the creation of reliable propulsion systems. While current spacecraft rely primarily on chemical propulsion, which is effective for reaching orbit, this method falls short for deeper space travel. As humanity looks to explore the outer reaches of the solar system and beyond, researchers are focusing on propulsion techniques such as ion thrusters and solar sails. These technologies promise to provide continuous thrust with far less fuel, making interplanetary journeys not only more efficient, but also more feasible. Safety in space also hinges on the development of advanced life support systems capable of sustaining human life for extended periods in the harsh conditions of space. These systems must efficiently recycle air and water, manage waste, and maintain habitable conditions for astronauts far from Earth. Innovations in bioregenerative life support, systems that mimic Earth's ecosystems, are being explored as potential solutions. These systems use plants and microorganisms to create self-sustaining environments, crucial for long-duration missions, such as potential journeys to Mars. These technological strides are not merely theoretical. They represent the next vital steps in humanity's journey to explore the stars, ensuring that we are prepared to venture into the unknown for years to come. Space exploration has always been a symbol of human ambition, pushing the boundaries of what we know. And yet, as we venture further into the cosmos, we face profound challenges that demand innovative solutions. Among these, advancements in radiation protection technology are absolutely vital for ensuring the health and safety of astronauts. Space is inherently filled with cosmic radiation, an invisible but potent force that poses significant health risks to those traveling beyond Earth's protective atmosphere. Without the shielding of our planet's magnetic field, the further we travel into space, the greater the exposure to high-energy particles from sources like solar flares and cosmic events. Developing shielding materials that are not only effective in protecting astronauts from this radiation, but are also lightweight and robust enough to be used on spacecraft is a monumental challenge. Research is already underway into novel materials and protective designs that aim to minimize radiation exposure while ensuring that astronauts' mobility and comfort are not compromised. These advancements in radiation protection are crucial for the future of space travel, as they will allow us to push deeper into space to destinations like Mars or even beyond, without the looming threat of radiation-induced health issues, such as cancer and long-term organ damage. In addition to radiation protection, communication technology must undergo significant upgrades to meet the demands of deep space exploration. Currently, the methods we use to communicate with spacecraft often result in delayed transmissions when they are far from Earth. This delay is particularly problematic for astronauts on long-duration missions, where real-time communication could be critical not only for mission success, but also for maintaining the mental and emotional well-being of the crew. By enhancing relay satellites and establishing a more interconnected network in space, we can ensure more reliable, real-time communication. This will make it easier to stay in touch with Earth, improving the support systems for astronauts and helping them manage the isolation and stress that come with extended space missions. As space tourism moves closer to becoming a reality, especially in the context of deep space, concerns surrounding safety and well-being will multiply exponentially. Deep space, defined as the vast expanse beyond Earth's immediate vicinity, presents a host of challenges that differ drastically from those encountered during suborbital flights or even trips to low Earth orbit. The environment in deep space is far more hostile. Travelers will encounter cosmic radiation, unpredictable microgravity, and the psychological strain of long-duration space travel, all of which can significantly impact human health and safety. Cosmic radiation is one of the most concerning risks, as it can increase the likelihood of developing cancers or other serious health conditions. In low Earth orbit, astronauts are shielded by Earth's atmosphere, but beyond this protective shield, they are vulnerable to the dangers of high-energy particles that constantly bombard the cosmos. As humanity moves further into space, developing effective radiation shielding and real-time monitoring systems will be of paramount importance, particularly as space tourists venture to destinations such as Mars or farther out into the solar system. Beyond physical health, the psychological effects of long-duration space travel present an equally formidable challenge. The isolation, confinement, and limited social interaction aboard a spacecraft can lead to significant mental health issues. Over time, stress, anxiety, and even depression can take hold of astronauts, and interpersonal conflicts among the crew can further exacerbate these problems. The psychological strain of space travel has been well documented on shorter missions, but it becomes an even greater concern for trips that might last months or even years. Ensuring that astronauts are properly trained, have access to psychological support, and can maintain communication with loved ones on Earth will be essential for the long-term success of deep space tourism. Another critical concern is the reliability of life support systems, propulsion technologies, and redundancy protocols. In the vast and remote expanse of deep space, help is not a simple phone call away. If a spacecraft malfunctions or an emergency arises, immediate assistance will not be possible. This means that life support systems must be designed to operate flawlessly for long periods without fail. Additionally, spacecraft must be equipped with advanced technologies capable of addressing unforeseen contingencies and ensuring that astronauts' health and safety are maintained in the event of a malfunction. The challenges facing deep space tourism are vast, but they are not insurmountable. As technology advances and solutions are found to address these critical issues, we move closer to unlocking the potential of deep space as the next great frontier for humanity. However, it is clear that before we can embark on such daring ventures, ensuring the safety of those who venture into the unknown must remain the top priority. As we set our sights on Mars, the possibility of terraforming this distant world opens up an entirely new realm of possibilities for human habitation. Terraforming Mars, the process of altering its environment to make it more Earth-like, could transform the red planet into a viable destination for human life. With breathable air, liquid water, and a more temperate climate, Mars could serve as a backup home for humanity in the event of catastrophic events on Earth, such as climate disasters or asteroid impacts. Beyond its potential as a refuge, terraforming Mars would also represent a massive leap forward in our understanding of planetary science and engineering. The techniques and technologies developed to modify the Martian environment could be adapted for use on other celestial bodies, laying the groundwork for future missions to distant planets and moons. In time, we might even be able to terraform other planets in our solar system, expanding humanity's reach beyond Earth and proving that life can not only survive, but thrive beyond our home planet. The cultural impact of terraforming is equally profound. It raises important ethical questions about ownership, stewardship, and our right to alter another world. As humanity gains the ability to change the environment of an entire planet, it will be forced to reconsider its relationship with the cosmos, leading to deeper reflections on sustainability and the responsible use of our resources. The questions that arise from terraforming Mars could have far-reaching implications, not only for how we approach other planets, but also for how we manage and protect the Earth itself. As humanity's capabilities continue to grow, the prospect of terraforming ignites curiosity about the possibility of life beyond our solar system. Could other civilizations in the universe be attempting similar projects? As we take steps towards making Mars habitable, we may also be moving closer to answering some of the most fundamental questions about the nature of life in the universe and our place within it. With each advancement, we are reminded that we are not just explorers, but pioneers, charting a course for future generations to follow and to continue the quest for knowledge that defines the human spirit. Lastly, the concept of sustainable living in space is becoming increasingly important as we look to establish a long-term presence beyond Earth. Space is a harsh and unforgiving environment, filled with radiation, microgravity, and extreme temperatures. To thrive in such a setting, humanity will need to develop innovative solutions for creating self-sustaining habitats that protect us from these dangers, while also making efficient use of available resources. The development of advanced life support systems, such as those that can recycle air and water, will be key to sustaining long-term missions. Hydroponic and aeroponic farming techniques, which allow for the cultivation of food without soil, will also play a critical role. These methods use less water and space than traditional agriculture, making them ideal for space environments where resources are limited. Not only will these systems provide astronauts with the nourishment they need, but they will also help to maintain the necessary oxygen levels in the habitat, ensuring that all aspects of human life in space can be sustained. As we move toward these ambitious goals, we are reminded that the journey into space is not just about exploration. It is about survival and the creation of new opportunities for humanity. The challenges are vast, but so too is the potential for growth, discovery, and transformation. The future of space exploration depends not only on technology, but on the ability to envision a new way of living and thriving beyond Earth in the harshest and most inhospitable environments we can imagine. Energy management is an indispensable factor in the pursuit of sustainable living in space. As humanity ventures farther into the cosmos, one of the primary challenges is ensuring a reliable, long-term power supply for astronauts aboard spacecraft and space stations. Solar panels have long been the go-to energy source, capturing sunlight and converting it into usable power. However, these panels must be optimized to maximize efficiency, as they are often the sole power source for missions. To overcome the limitations of solar energy, especially for deep space exploration, innovations in energy storage become paramount. Advanced battery technologies are one potential solution, allowing astronauts to store energy for times when sunlight is unavailable. Furthermore, exploring the use of nuclear power could offer a more consistent and potent energy supply for longer missions, including those beyond our solar system. As we look to the future, developing lightweight, durable materials is crucial for the construction of spacecraft and habitats. Materials science innovations are already paving the way for substances that can withstand the harsh conditions of space, such as extreme temperatures, radiation, and the vacuum of space, while still being light enough to transport efficiently. This marriage of strength and weight savings plays a critical role in sustainable living and exploration, as it reduces the cost and complexity of space travel. Another cornerstone of sustainability is fostering a circular economy, even in the vacuum of space. Waste management will be one of the most significant challenges of long-term space missions. The waste produced by astronauts, whether in the form of human waste, food scraps, or used equipment, must be minimized and repurposed to ensure that resources are not wasted. One possible solution is converting human waste into usable materials, such as fertilizers for growing food or even energy through biological processes. By adopting a circular approach where waste is continually reused, we can reduce the dependency on Earth for supplies, making long-term space exploration more feasible. These sustainable practices are not merely theoretical. They are the key to ensuring that space exploration is not a fleeting endeavor, but a long-term project that supports humanity's expansion beyond Earth. If we are to establish permanent settlements on other celestial bodies like Mars, the ability to live off the land, utilizing in situ resources, is paramount. This process of creating self-sustaining colonies is vital for missions that could last decades or more. The development of artificial intelligence, AI, and its applications in space research and hazard mitigation is becoming increasingly important. AI systems have proven invaluable in analyzing vast amounts of data, something that human researchers simply cannot accomplish at the same speed or scale. These sophisticated tools are integral in tracking, predicting, and even preventing space hazards. By using machine learning algorithms, AI can detect patterns in the behavior of asteroids, comets, and other space debris that might pose a threat to Earth or to space missions. For instance, AI can predict the trajectory of potentially hazardous asteroids with remarkable precision, providing early warnings that can lead to mitigation strategies. AI's role extends beyond just tracking space objects. It is also helping scientists understand the impact of solar flares, space weather, and other celestial phenomena that could disrupt communications, navigation, and weather forecasting systems here on Earth. Solar storms and radiation can pose significant risks to satellites and space stations, so being able to predict when and where these events might occur is crucial to safeguarding our infrastructure. By analyzing historical data on solar activity, AI systems can enhance the protection of these vital technologies. In addition to protecting satellites, AI has become a key player in planetary defense. Researchers are using AI to simulate various impact scenarios, testing strategies for deflecting or disrupting asteroids that could potentially strike Earth. This powerful computational tool gives scientists the ability to test a range of strategies, from nuclear deflection to kinetic impactors, without the need for real-world experimentation. As AI continues to evolve, the ability to predict and prevent space hazards will improve, providing humanity with better tools to protect our planet from cosmic threats. These AI-driven advancements in space research extend far beyond just disaster prevention. They represent a partnership between human creativity and computational power, one that promises to yield new insights into how we can navigate the complexities of space. As machine learning, data analysis, and AI technology continue to advance, our capacity to explore space and defend our planet will expand. The collaboration between humans and AI is shaping the future of space exploration, turning what was once science fiction into an attainable reality. The discovery of extraterrestrial life, should it occur, would be one of the most profound breakthroughs in human history. Such a discovery would challenge our understanding of life's origins and potentially redefine humanity's place in the universe. It could prompt a paradigm shift on Earth, leading to a deeper sense of unity among nations and cultures as we grapple with our shared existence in a vast and diverse cosmos. The implications of finding life beyond Earth would extend well beyond science, influencing philosophy, religion, and international relations. In addition to the intellectual and philosophical implications of space exploration, the practical benefits of new resources from space could revolutionize the global economy. For example, mining asteroids for precious metals or extracting water from lunar deposits could alleviate some of the pressure on Earth's finite resources. This could diminish competition for terrestrial resources and reduce conflicts arising from scarcity. Moreover, such resources could drive the creation of entirely new industries, transforming the economic landscape. As space exploration expands, it could lead to the development of new technologies that have far-reaching implications for life on Earth. Innovations born from space research often find their way into everyday life, driving advancements in fields like medicine, materials science, and computing. Space travel technologies have historically led to breakthroughs that improve infrastructure, healthcare, and communication systems. These developments not only enhance our capacity to explore space, but also elevate the quality of life for people on Earth. The potential for human colonization of other celestial bodies such as Mars or the Moon could also change the way nations interact with one another. The question of ownership, who controls the Moon or Mars, could spark international debates about governance, cooperation, and shared responsibility. As humanity considers the possibility of settling on other planets, the traditional notion of national borders could blur, giving rise to new models of cooperation and shared governance in space. The future of space exploration is, therefore, inextricably linked to the future of human society and our evolving role in the cosmos. As we continue to develop technologies that detect and prevent space threats, the urgency to protect our planet becomes more apparent. Near-Earth objects, such as asteroids and comets, remain a persistent danger, and advancements in detection technology are crucial for safeguarding our world. Ground-based telescopes, equipped with advanced sensors, are now being used to track these objects with greater precision, enabling scientists to spot even smaller asteroids that could previously have gone undetected. By using infrared telescopes, astronomers can detect the heat emitted by celestial bodies, allowing them to identify objects hidden in the sunlight. The Pan-STARRS and Catalina Sky Survey are just two of the many initiatives that have greatly enhanced the cataloging of near-Earth objects. These projects are integral to the systematic monitoring of potentially hazardous objects, providing us with the tools necessary to track and respond to space threats. Through these efforts, humanity is better prepared to defend itself against the ever-present dangers lurking in the depths of space. With continued advancements in technology and international collaboration, we can ensure that space exploration remains a vital and safe endeavor, not just for the astronauts aboard our spacecraft, but for all of humanity. Furthermore, space missions, such as NASA's Near-Earth Object (NEO) program, have taken on a more pivotal role in strengthening humanity's defense against cosmic threats. These initiatives focus on enhancing our ability to detect and track objects that could potentially harm Earth, with the goal of improving the accuracy of predictions related to their paths. As detection technologies continue to advance, so too do the strategies for preventing catastrophic encounters with these celestial bodies. Among the many techniques under investigation, one of the most promising is the use of kinetic impactors. Kinetic impactors work by sending a spacecraft to collide with an asteroid at high speeds, altering its trajectory just enough to avoid a direct collision with Earth. NASA's Double Asteroid Redirection Test (DART mission serves as a groundbreaking experiment in this area, actively testing the feasibility of such planetary defense mechanisms. The goal of this mission is to change the orbit of an asteroid, proving that this method could be applied in the future to protect Earth from an impending impact. The DART mission exemplifies humanity's growing commitment to planetary defense and its ability to think beyond Earth's atmosphere. Another intriguing concept under research is the idea of using gravity tractors. This technique involves sending a small spacecraft to hover near an asteroid, exerting gravitational forces on it over time, thereby gently nudging the object off its original path. Although this approach is more theoretical at present, it offers a gentler alternative to high-velocity impacts, providing a slower but potentially more precise way of altering the course of an asteroid. The combined efforts of detection technologies and innovative prevention strategies mark a significant leap forward in humanity's ability to confront the cosmic threats that lurk at the edges of our solar system. As these technologies continue to evolve, humanity's approach to protecting our planet from space-based dangers grows ever more sophisticated. Simultaneously, scientists recognize that traveling to other stars is one of the most formidable challenges humanity will ever face. As we peer deeper into the cosmos, the vast distances between us and even the closest stars become evident. For instance, Proxima Centauri, the nearest star to our solar system, is more than 4 light-years away, a journey that, with today's spacecraft, would take tens of thousands of years. Despite this daunting reality, researchers are actively exploring revolutionary ideas to overcome these immense distances and make interstellar travel a tangible goal. One of the most exciting concepts currently being explored involves propulsion systems far beyond our current technological capabilities. Solar sails, for example, harness the pressure of sunlight to propel a spacecraft through space using no fuel but the power of the sun. Even more radical ideas, such as the concept of a warp drive, which theoretically bends space-time itself, are being examined by scientists. If successfully developed, these technologies could drastically reduce the travel time to distant stars, transforming what seems like a far-fetched science fiction dream into a feasible reality. In parallel, advancements in robotics and artificial intelligence are critical for enabling interstellar missions. These missions would require spacecraft capable of autonomous operations, potentially lasting for decades or even centuries. As we venture farther from Earth, it will be crucial to develop self-sustaining systems that can maintain life support and conduct scientific research without relying on direct intervention from Earth-based teams. In this context, the concept of generation ships becomes increasingly relevant. Spacecraft designed to support human life over multiple generations as they travel to distant star systems. These ships would carry entire cultures, fostering new societies and pushing the boundaries of human exploration. The pursuit of interstellar travel is not just about reaching distant worlds. The technologies and innovations being developed for this purpose have the potential to benefit life on Earth as well. The advances in material science, energy production, and propulsion technologies could revolutionize industries across the globe, leading to breakthroughs in everything from energy efficiency to sustainable living. As research in these fields continues, the dream of reaching other stars also inspires optimism about the future of life on Earth, igniting curiosity and fueling the imagination of those working on these groundbreaking projects. Space agencies worldwide are undertaking increasingly ambitious, long-term missions designed to enhance our understanding of the cosmic forces that could pose a threat to Earth. One of the most captivating initiatives in this regard is the mission dedicated to studying near-Earth asteroids. These missions aim to track and characterize the trajectories of asteroids, providing vital information that will help develop strategies for mitigating potential hazards they may pose in the future. By better understanding the behaviors and paths of these objects, scientists hope to create more accurate models for predicting their movements and devising effective defense strategies. In addition to asteroid tracking, solar phenomena are another significant focus of these missions. The Sun, with its solar flares and coronal mass ejections, can wreak havoc on technological infrastructure here on Earth. These bursts of energy can disrupt communication systems, damage satellites, and even interfere with power grids. To mitigate these risks, advanced spacecraft are being deployed, equipped with state-of-the-art instruments to monitor solar activity in real time. By collecting and analyzing data on solar flares and coronal mass ejections, researchers will be able to more accurately predict space weather via providing early warning systems to protect our technological infrastructure from solar-induced disruptions. Other upcoming missions will focus on the observation of gamma-ray bursts and supernova, two of the most catastrophic events in the universe. These powerful cosmic phenomena release vast amounts of energy, and if they occur too close to Earth, their effects could be devastating. By studying the conditions that lead to these explosive events and tracking their occurrences across the universe, scientists aim to better understand the underlying physics that drives them and identify any potential risks they may pose to our planet. At the heart of these initiatives lies the importance of international cooperation. Space agencies from around the world are collaborating on the development of early warning systems which could provide humanity with crucial alerts in the event of imminent cosmic threats. These missions, supported by advancements in technology, data analysis, and international collaboration, will play an essential role in ensuring humanity's safety as we continue to explore and navigate the vast, unpredictable cosmos. As humanity looks toward the stars, it is essential to recognize the many risks that could accompany long-duration space travel. Cosmic radiation, for instance, poses a significant health threat to astronauts. In deep space, they are exposed to higher levels of radiation than what we experience on Earth. Prolonged exposure to this radiation increases the risk of cancer and other health complications, making it essential to develop protective shielding for spacecraft and to explore potential medical countermeasures. In addition to physical health risks, the psychological challenges of long-term space missions must also be addressed. Isolation, confinement, and the absence of natural light can take a toll on astronauts' mental and emotional well-being. Preparing for these challenges is crucial to the success of long-duration space travel. Research into astronaut psychology, combined with advancements in training and support systems, will ensure that our pioneers can withstand the mental and emotional stresses of extended journeys through deep space. Ultimately, the pursuit of interstellar travel and the exploration of distant stars will require not only technological breakthroughs, but also a deep understanding of the human condition. It will push the limits of human endurance and innovation while sparking new avenues of scientific discovery. The challenges may seem insurmountable, but as we continue to explore the cosmos, each step forward brings us closer to a future where humanity can reach for the stars, unlocking the mysteries of the universe and securing a place for ourselves among them. Dark matter, a substance both invisible and enigmatic, stands as one of the most captivating riddles in modern astrophysics. Its elusive nature not only fuels intrigue, but also challenges the very foundation of our understanding of the universe. Though invisible to our eyes, dark matter is believed to constitute roughly 27% of the total mass and energy content of the cosmos. Despite its vast presence, it remains undetectable by traditional astronomical methods. It neither emits, absorbs, nor reflects light, making it impervious to conventional means of observation. This absence of interaction with electromagnetic radiation leaves scientists with little more than its gravitational effects to study, yet these effects have proven profound. The presence of dark matter suggests there could be forms of matter or forces within the universe beyond what we currently understand. It beckons the possibility that new particles not yet observed might be at play. These particles could be entirely alien to our current knowledge of the universe's building blocks, potentially opening the door to discoveries that could completely redefine particle physics. As researchers delve deeper into the nature of dark matter, it is likely that they will uncover phenomena that push the boundaries of the standard model of particle physics, the established framework that currently governs our understanding of fundamental forces and particles. This pursuit of understanding might even ignite a shift in the scientific paradigm, as new discoveries challenge or expand upon core concepts like the nature of matter, energy, and the fundamental forces of the universe. As it stands, dark matter's primary known interaction is through gravity, yet it hints at much more. Could this elusive substance be tied to other unexplored forces in nature? Could it reveal new connections between gravity and the other fundamental forces, such as electromagnetism or the weak and strong nuclear forces? It is through studying dark matter's gravitational influence, particularly in galaxies and galaxy clusters, that scientists can begin to unlock the mystery behind its properties and behaviors. Exploring how dark matter behaves in different cosmic environments could also lead to breakthroughs in understanding gravity itself. There are hints that dark matter might challenge or refine Albert Einstein's general theory of relativity, and possibly even guide us toward a unified theory of quantum gravity, a framework that seeks to combine the seemingly incompatible theories of general relativity and quantum mechanics. Such a discovery would mark a revolution in theoretical physics and deepen our understanding of the universe's most fundamental workings. Yet, this journey is only beginning. The tools and technologies needed to peer further into the mysteries of dark matter are advancing rapidly. With the development of more sensitive detectors, cutting-edge telescopes, and enhanced computational models, we are slowly but surely gaining the ability to explore this cosmic enigma in ways previously unimaginable. The search for dark matter could eventually lead us to an entirely new realm of physics, one that holds the potential to transform not just our understanding of the universe, but of our place within it. The implications of such a discovery are profound, possibly offering new insights into the universe's origins, its current state, and its eventual fate. The very nature of reality itself could be redefined. However, while the secrets of dark matter might reveal new possibilities for advancing science, They also open the door to a range of exciting yet dangerous prospects, especially in the realm of energy manipulation. One of the most promising and potentially world-altering areas of exploration lies in harnessing the energy produced by stars, particularly through nuclear fusion, the same process that powers our sun. If humans could replicate this process on Earth or in space, it might provide a nearly limitless source of energy, one that could dramatically reduce our reliance on fossil fuels and usher in an era of sustainable energy. Fusion could also provide the key to advancing space exploration. Imagine spacecraft powered by the same energy that fuels stars. Space travel could become far more efficient and far-reaching. The possibilities for interstellar travel would be significantly expanded, offering a new frontier for human exploration beyond our solar system. Additionally, there are theories that suggest the exploitation of other exotic forms of energy, such as zero-point energy or dark energy, could further revolutionize technology. Zero-point energy, grounded in quantum mechanics, refers to the energy that exists even in the vacuum of space due to fluctuations at the subatomic level. If harnessed, it could provide a virtually infinite energy source, radically changing the way we think about power. Even more mysterious is dark energy, which makes up approximately 70% of the universe's total energy content. Though its nature remains one of the greatest mysteries in physics, understanding and harnessing dark energy could enable humanity to explore the cosmos in ways never before thought possible. It might even allow us to manipulate the very expansion of the universe itself, unlocking a power capable of shaping the cosmos. As enticing as these scientific breakthroughs are, they come with a host of ethical considerations. The ability to control and manipulate energy at such unprecedented scales could lead to geopolitical tensions and conflicts over resources. Nations or powerful organizations might vie for control over energy-rich celestial bodies, leading to disputes over who gets access to the vast resources of space. These concerns underscore the importance of international collaboration and cooperation. As we explore the potential of space energy, it is essential that humanity works together to ensure these discoveries benefit all people, not just a select few. Ethical frameworks and agreements will be crucial in managing the responsible use of space resources to ensure that the pursuit of knowledge and power does not lead to unintended harm or inequality. The path ahead is both thrilling and uncertain, as the pursuit of dark matter, fusion energy, and other cosmic phenomena promises us to push the boundaries of what we understand about the universe. With each step forward, we move closer to unlocking the deepest secrets of the cosmos, secrets that could alter the course of human history and reshape our place in the vast expanse of space. The development of new energy sources holds the promise of radically transforming humanity's ability to protect Earth from cosmic threats, marking a profound step toward the safeguarding of our planet. With advancements in energy efficiency, we could create systems capable of monitoring and neutralizing asteroids or comets that might pose a risk to our world. These technologies, born from innovative energy forms, may not only protect us from such dangers, but also pave the way for humanity's survival beyond Earth. By enabling the colonization of distant planets, they offer a crucial avenue for securing humanity's future as we confront environmental, political, and existential challenges on our home planet. The prospect of mastering new energy forms, particularly in the vast expanse of space, challenges our technological imagination. It invites us to reconsider the future of human civilization, fueling both excitement and a profound sense of responsibility as we extend our reach into the cosmos. This invitation to explore new frontiers is paralleled by our ever-present curiosity about the end of the universe. Theories surrounding this final chapter of existence stir a deep emotional response in us. On one hand, they ignite our imagination and drive us to venture into the farthest corners of time and space. Concepts like the heat death of the universe, the Big Crunch, or a cosmic freeze challenge not only our scientific understanding, but also force us to confront our most profound existential questions. What happens when all stars burn out? How will life evolve, or perhaps cease to exist, when the cosmos undergoes irreversible transformations? These questions stir a sense of wonder but also dread, reminding us of the limits of our knowledge. The scale of time involved, spanning millions, even billions of years, can be staggering. It forces us to reckon with our mortality, the impermanence of our lives, and the eventual disappearance of everything we know and cherish. The thought of a cold, lifeless universe, devoid of stars and planets, can turn awe into fear, compelling us to reflect on our place in the universe and the fleeting nature of existence. The vastness of cosmic time challenges us to look inward, to question our legacy, and to contemplate what we can do with the time we have. In this way, the contemplation of the universe's eventual end mirrors the dual nature of human curiosity. It pushes us to explore, even as it reminds us of the limits of our existence. As we engage with these theories, they invite us to find meaning and significance in the present, to appreciate the ephemeral beauty of life that we often take for granted. Though the ideas of cosmic finality may provoke feelings of dread, they also challenge us to live with purpose. The inevitable end of the universe might inspire us to find joy in the transient nature of our existence and to seek out experiences that contribute to our understanding of life's purpose. The pursuit of knowledge, fueled by this curiosity, may ultimately guide us toward a deeper connection with the cosmos and our place within it. One of the more intriguing intersections of theoretical physics lies in the idea that black holes may not be the absolute enigma they were once thought to be. For decades, these cosmic giants were believed to possess an impenetrable event horizon, beyond which nothing, neither matter nor information, could escape. However, recent advancements in quantum mechanics and general relativity, particularly those proposed by the legendary physicist Stephen Hawking, have started to unravel this notion. The concept of Hawking radiation, for example, suggests that black holes can emit particles due to quantum effects near their event horizons, meaning that information may, in fact, slowly leak out as the black hole evaporates over astronomical timescales. This groundbreaking idea challenges our understanding of physics and opens the door to profound implications. The possibility that black holes leak information raises crucial questions about the nature of entropy and the laws of thermodynamics, particularly as they apply in the extreme environments of black holes. If information escapes from a black hole, it suggests a deeper connection between the fabric of space and time itself, offering insights into the most fundamental aspects of our universe. This idea supports the holographic principle, which posits that the universe we experience in 3 dimensions might actually be a projection of information encoded on a 2-dimensional surface. Such a revelation would not only deepen our understanding of black hole mechanics, but could also lead to a revolutionary new framework for understanding space, time, and reality itself. As scientists continue to explore this theory and refine their models, they may uncover the true nature of the universe's most enigmatic objects. The reconciliation of black holes with quantum theory could lead to breakthrough discoveries, bringing us closer to uncovering the ultimate unity of the cosmos. This exploration not only stimulates our curiosity, but could also reshape our understanding of the very fabric of reality, offering us a glimpse into the profound mysteries of the universe. On a more practical level, the phenomenon of time dilation, predicted by Einstein's theory of relativity, holds significant implications for space exploration. Time dilation reveals that time is not a universal constant, rather it is relative, changing based on an object's speed and the strength of gravitational fields. For astronauts venturing into deep space, especially at speeds approaching significant fractions of the speed of light, this effect could alter their perception of time. For them, a journey that might last only a few years could span many more years on Earth. This presents a unique challenge for long-duration space missions, not just in terms of the physical challenges involved, but also in the psychological and social impact on astronauts who experience time differently than those they leave behind. As we contemplate the possibility of space travel at relativistic speeds, time dilation also forces us to rethink our ideas about distance and travel time. While traveling to distant stars may seem within reach if we could achieve such speeds, the reality of time dilation presents new questions. How do we manage communication between Earth and these far-off missions? What happens when generations of people are born and live their entire lives in space, never returning to Earth? These questions transform the very nature of human relationships, both in terms of how we understand our connection to Earth and how we maintain contact with loved ones across immense distances. Integrating the understanding of time dilation into our space exploration plans is essential for improving the safety and well-being of astronauts and ensuring the success of future missions. As we push beyond Earth's orbit, we must consider not just the physical aspects of space travel, but also the complex psychological and social dynamics that come with time travel at relativistic speeds. This understanding will shape the future of human exploration among the stars as we redefine what it means to travel through time and space. Among the many mysteries of the cosmos lies the concept of rogue black holes. Those black holes that drift through the vastness of space without being anchored at the centers of galaxies. These celestial wanderers offer a fascinating insight into the dynamic processes that shape galaxies and the life cycles of black holes themselves. When galaxies collide, a frequent occurrence in the universe, the gravitational forces involved can eject black holes from their host galaxies, sending them on solitary journeys through intergalactic space. Without the gravitational pull of a galaxy to bind them, these rogue black holes wander independently, potentially wreaking havoc on the stars and systems they encounter along the way. The exploration of rogue black holes, as well as the other phenomena we are only beginning to understand, deepens our understanding of the universe's complexity and reminds us that the cosmos is filled with mysteries yet to be uncovered. As we continue to explore space, our curiosity drives us toward answers that may reshape our understanding of not just the cosmos, but our place within it. Every new discovery, every theory tested and refined, brings us one step closer to unraveling the fundamental truths of existence itself. Gravitational waves have emerged as one of the most groundbreaking phenomena in modern astrophysics, providing compelling evidence for the existence of black holes merging in locations that were once deemed unexpected. These extraordinary events suggest that black holes are capable of forming in isolation, potentially arising from the collapse of massive stars that end their lives in supernova explosions, far removed from the familiar environments of galactic centers. Each new detection of a black hole merger brings fresh insights into the existence of what are now known as rogue black holes, solitary giants that may roam freely through the vast expanses of the cosmos. The discovery of these rogue black holes is not just a matter of academic curiosity. Their existence could help explain some of the most puzzling cosmic phenomena. For example, they might offer a resolution to the mystery of missing mass in the universe. Rogue black holes could account for some of the gravitational effects observed in deep space, effects that are detectable but whose sources remain hidden due to the immense distances involved and the black hole's inherent darkness. As scientists continue to refine their detection methods, particularly through the growing field of gravitational wave astronomy, the search for these elusive wanderers intensifies. The future of astrophysics is inexorably tied to the quest for a deeper understanding of rogue black holes, which could ultimately reshape our understanding of galaxy formation and evolution. Rogue black holes might be central to the gravitational interactions that shape galaxies, potentially influencing the dynamics of galactic mergers and the formation of large-scale cosmic structures. These solitary black holes, moving freely through space, could shed light on the processes that govern the evolution of galaxies and the structure of the universe itself. Their very existence challenges our conception of black holes as objects confined to the centers of galaxies, suggesting that the universe might be teeming with hidden players whose influence we are only just beginning to understand. They are the embodiment of the mysteries that lie at the heart of astrophysical research, bridging the gap between the known and the unknown. As we probe further into the cosmos, one concept that captivates both the scientific community and the public alike is the possibility of wormholes, hypothetical structures that could provide shortcuts across the fabric of space-time. A wormhole is often described as a tunnel connecting two distinct points in space and time, theoretically allowing for near-instantaneous travel between distant regions of the universe. Rather than journeying across the vast, empty expanse that separates stars or galaxies, a spacecraft might enter one end of a wormhole and emerge almost instantaneously at its other end. bypassing the intervening space entirely. This concept arises directly from Einstein's theory of general relativity, which revolutionized our understanding of gravity and spacetime. According to general relativity, matter bends the fabric of spacetime around it, and wormholes can be viewed as extreme curvatures or distortions of this fabric. While the mathematics behind wormholes suggests they could exist, no empirical evidence has yet been found to confirm their presence. Theoretical models propose that these tunnels could act as shortcuts, providing ways to travel vast distances in the universe without the need for conventional, time-consuming methods of propulsion. However, such travel remains speculative. The implications of wormholes extend far beyond mere transportation. If we could manipulate the ends of a wormhole, it might even open the door to time travel, allowing us not only to journey across space, but also through time. This tantalizing possibility raises profound questions about the nature of causality, the flow of time, and the very structure of reality. Could we witness historical events firsthand, or even alter the future by manipulating the fabric of time itself? Despite the allure of these concepts, traveling through a wormhole presents significant challenges. Issues of stability, how to keep the wormhole open long enough to pass through, and the need for exotic matter to prevent collapse highlight the limitations of our current understanding of physics. Nevertheless, the pursuit of wormholes pushes the boundaries of our knowledge about space and time, encouraging us to consider new ways of understanding the universe. Though we remain far from practical applications, the exploration of wormholes represents a thrilling frontier in theoretical physics, one that expands our comprehension of the cosmos and challenges our deepest assumptions about the nature of reality. In addition to the mysteries of black holes and wormholes, one of the most profound questions facing humanity is the possibility of intelligent extraterrestrial life. For centuries, humans have viewed themselves as the pinnacle of intelligence and capability in an otherwise empty universe. Our perspective has been predominantly anthropocentric, with humanity seeing itself as the central figure in the cosmic story. The discovery of extraterrestrial intelligence would force us to reassess this view, confronting us with the realization that we may not be alone in the universe. Such a discovery could have profound implications, not only for science, but for philosophy, religion, and our understanding of our own existence. The revelation of intelligent life beyond Earth would challenge the foundations of many belief systems that place humans at the center of creation. The questions it raises would be as philosophical as they are scientific. What is the nature of creation? Does the existence of extraterrestrial intelligence imply a higher power? What does it mean to be human in a universe where other sentient beings exist? These questions would undoubtedly spark debates among theologians, scientists, and philosophers, leading to new dialogues that could redefine our collective understanding of humanity's place in the grand cosmic scheme. From a scientific standpoint, the discovery of extraterrestrial intelligence would fundamentally alter our approach to biology, astrobiology, and evolutionary theory. The existence of alien life forms would force us to reconsider what constitutes life itself. How might life evolve under conditions vastly different from those on Earth? Could parallel evolutionary pathways exist, leading to forms of intelligence that are unlike anything we can imagine? These inquiries would not only expand our definition of life, but could also offer new insights into the potential for other life forms in the universe. The implications of such a discovery would be truly revolutionary, reshaping our understanding of life, intelligence, and our place in the cosmos. The prospect of discovering intelligent extraterrestrial life would inevitably have profound implications for international relations. Contact with civilizations beyond Earth could either foster global unity or ignite conflict, depending on how nations respond. This could become a defining challenge for humanity, requiring unprecedented cooperation. As we confront the reality of intelligent life elsewhere, it may compel us to reevaluate our place in the cosmos, forcing us to work together on a scale never seen before. An encounter with extraterrestrial intelligence might trigger radical shifts in our thinking, pushing us to embrace new perspectives that alter our view of life, existence, and our role in the universe. At the cutting edge of transforming our understanding of space and space exploration are speculative technologies that could change everything we know about the cosmos. One such concept is the warp drive, a theoretical propulsion system that could potentially allow faster-than-light travel. By bending or warping the very fabric of space-time around a spacecraft, this technology would make distant star systems accessible, vastly expanding our reach in the universe. If realized, warp drives could revolutionize space exploration, bringing previously unreachable destinations within our grasp. Another breakthrough on the horizon is the development of advanced quantum communication systems. Unlike traditional communication methods that are limited by the speed of light, quantum communication harnesses the strange principles of quantum entanglement to transmit information instantaneously, no matter the distance. This capability could radically enhance space exploration, enabling real-time communication across vast cosmic distances without the time delays imposed by light speed limits. It could be a game changer for missions to distant worlds, ensuring constant, immediate contact with Earth. The role of artificial intelligence, AI, is also crucial in the evolving landscape of space exploration. As AI systems become more adept at understanding celestial phenomena, they will take on increasingly complex tasks in autonomous navigation and exploration. These machines could analyze data from far-off planets or stars, executing intricate operations without human intervention. Not only would this assist human-led missions, but AI could also pave the way for an entirely new generation of robotic explorers, capable of operating independently across the cosmos, uncovering the mysteries of the universe. The potential to harness dark energy presents yet another frontier of exploration. Dark energy is a mysterious force, believed to be responsible for the accelerated expansion of the universe, yet it remains poorly understood. If we could unlock its secrets and manipulate this energy, it might revolutionize propulsion technology or even lead to entirely new forms of energy generation. The study of dark energy could hold the key to many of the universe's most profound mysteries, and mastering it may open up untold possibilities for humanity's future in space. As we venture further into the cosmos, advanced simulations play a pivotal role in enhancing our understanding of the universe. These powerful tools allow scientists to recreate and explore complex cosmic scenarios that would otherwise be impossible to observe directly. By using sophisticated computational models, researchers can simulate phenomena like black holes, supernovae, and even the early stages of the universe itself. These simulations are built on the fundamental laws of physics, enabling scientists to visualize and analyze events that occur on scales far beyond human comprehension. One of the primary benefits of these simulations is the ability to adjust variables and conditions in a controlled environment. Scientists can alter factors like gravity, matter density, and the presence of dark energy to see how these variables affect the evolution of cosmic structures. By doing so, they can test the limits of known physics, probing theoretical scenarios that challenge our understanding of reality. For instance, they can simulate the collision of two galaxies, or study how matter behaves in the extreme conditions near a black hole's event horizon. These investigations often lead to surprising discoveries, forcing scientists to rethink established theories and even propose entirely new ideas. The synergy between astronomical observations and computer simulations is essential for refining our understanding of the cosmos. When real-world data, such as the detection of gravitational waves from colliding black holes or the light from distant quasars, aligns with the predictions of simulations, it strengthens the credibility of both the experimental results and the underlying theoretical models. This collaboration enhances our comprehension of the universe, helping to unravel some of its most enigmatic phenomena. Astrophysicists continue to grapple with profound questions that challenge the limits of human knowledge. One of the greatest mysteries is dark matter, which makes up about 27% of the universe. Although we can infer its presence from gravitational effects, dark matter has yet to be directly observed. Its true nature remains one of the most elusive and debated topics in science. What is dark matter, and how does it interact with normal matter? Despite decades of research, no definitive answer has emerged, leaving scientists with a tantalizing mystery. Equally puzzling is dark energy, a force believed to be responsible for the accelerating expansion of the universe. Dark energy constitutes nearly 70% of the cosmos, yet its properties remain largely unknown. What is driving the expansion of the universe, and why is it accelerating at an ever-increasing rate? Understanding dark energy is crucial for constructing a comprehensive model of cosmic evolution and could dramatically alter our understanding of physics. The ultimate fate of the universe is another question that haunts scientists. Will the universe continue expanding forever, or will gravitational forces eventually bring about a cosmic collapse? Theories such as the Big Freeze, Big Rip, or Big Crunch offer different possible outcomes, each with its own implications for the future of everything we know. The timeline of the universe, along with its eventual end, raises important questions about the laws of physics, cosmology, and the fundamental nature of reality. In addition to these cosmic mysteries, the question of life beyond Earth remains one of the most profound existential inquiries. Scientists have discovered numerous exoplanets located within the habitable zones of stars similar to our Sun, yet the search for extraterrestrial life goes far beyond these discoveries. If life exists elsewhere, what form could it take? And perhaps more significantly, how would humanity respond to such a discovery? These questions not only inspire scientific exploration, but also challenge us to reconsider the uniqueness of life on Earth and our place in the vast, unexplored universe. Cosmic rays, high-energy particles traveling through space, offer another fascinating glimpse into the universe's mysteries. These particles, primarily composed of protons, but also including heavier nuclei and electrons, originate from diverse sources such as supernova, active galactic nuclei, and possibly even our own Sun. When cosmic rays interact with Earth's atmosphere, they create a cascade of secondary particles, some of which reach the ground. Studying cosmic rays provides valuable insights into high-energy processes occurring across the cosmos. The energy levels of these particles can reveal information about their origins, and when scientists detect particularly energetic cosmic rays, they often wonder which celestial event generated such immense energy. This leads to questions about potential unknown phenomena, opening up new avenues for exploration. By studying cosmic rays, scientists can deepen our understanding of mysterious objects like pulsars and black holes, while also seeking new sources of cosmic radiation that could further unravel the universe's secrets. As humanity continues its journey into space, the challenges ahead are as profound as they are exciting. Whether it's unlocking the secrets of dark matter, harnessing dark energy, or exploring the farthest reaches of the cosmos, we are standing at the threshold of an era of discovery. The technologies and simulations that enable us to explore these frontiers will shape the future of space exploration and perhaps even the future of humanity itself. With each new breakthrough, we edge closer to understanding not just the universe, but our place within it. Cosmic rays, those high-energy particles that constantly bombard Earth from all corners of space, might hold the key to unraveling some of the most profound mysteries of the universe. Although these particles are largely invisible to the naked eye, their impact on our understanding of the cosmos could be transformative. Through studying their paths and their interactions with matter, scientists have the potential to gain insights into some of the most elusive phenomena in space. For instance, cosmic rays can help researchers probe the interstellar magnetic fields that shape our galaxy. These fields play a critical role in the structure and dynamics of the Milky Way, and understanding them could unlock critical clues about the forces governing our cosmic neighborhood. By meticulously mapping the origins and trajectories of cosmic rays, scientists could also uncover vital information about the process of cosmic acceleration. This is the mechanism responsible for the high-speed motion of particles across vast distances, and understanding how it works could reshape our comprehension of both galactic and universal evolution. Furthermore, cosmic rays may even provide an unexpected pathway to studying dark matter and dark energy, two of the universe's most confounding and invisible components. If certain cosmic ray signatures are detected, it could indicate that these particles are interacting with forms of matter and energy that have thus far eluded our most advanced instruments. As technology continues to evolve, the potential to harness cosmic rays in new ways grows exponentially. New and improved methods for analyzing these particles could help shine a light on parts of the universe that remain hidden from current observational techniques. This could bring us ever closer to answering questions that have perplexed humanity for centuries, pushing the boundaries of what we know, and offering the promise of unprecedented breakthroughs in our understanding of the cosmos. Among the many enigmas that stretch across the universe, few captivate the human imagination quite like black holes. These regions of space, where gravity is so intense that not even light can escape, pose some of the most fundamental questions in astrophysics. How do black holes form? What are their internal structures like? And most intriguingly, what happens at the core of a black hole, where the laws of physics as we know them seemingly break down? The concept of singularities, points of infinite density at the center of black holes, only deepens this mystery. It's not just a scientific question, it's a philosophical one. What lies beyond the event horizon? This question tantalizes not only physicists, but also science fiction enthusiasts, fueling endless speculation about the nature of these extraordinary phenomena. Equally perplexing is the elusive nature of dark matter. While it makes up roughly 27% of the universe's total mass, it remains undetectable by traditional means. The only evidence for its existence comes from its gravitational effects on visible matter. Yet, despite decades of study, dark matter remains one of the most enduring mysteries in modern science. What exactly is it made of? Why has it been so difficult to detect? These questions continue to puzzle scientists, and the absence of definitive answers invites wild speculation about what might exist beyond our current understanding of matter and energy. But dark matter is only one part of the cosmic puzzle. The universe is also governed by a force known as dark energy, which is responsible for the accelerated expansion of the cosmos. Dark energy accounts for nearly 70% of the universe, yet its true nature remains a mystery. How can something so abundant and so influential remain so enigmatic? The expansion of the universe at an ever-increasing rate raises profound questions about the future of the cosmos. Is this acceleration leading us toward a big freeze, where galaxies drift so far apart that stars eventually burn out and the universe becomes a dark, cold place? Or could we be headed for a big crunch, where the expansion reverses, collapsing everything back into a dense, singular point? These questions not only fuel the curiosity of scientists, but also capture the imagination of anyone who gazes up at the night sky. The search for extraterrestrial life is another captivating aspect of modern scientific inquiry. With billions of galaxies scattered across the cosmos, each hosting billions of stars and likely countless planets, the possibility that life exists elsewhere seems almost too compelling to ignore. Whether through the hunt for microbial life on Mars or the search for signals from intelligent civilizations on distant exoplanets, humanity's quest to understand our place in the universe is an ongoing journey. This quest invites both scientific exploration and speculative imagination, as we ponder whether we are truly alone in the vast, uncharted expanse of space. A particularly intriguing mystery that has emerged in recent years is the concept of dark flow. This phenomenon, which refers to the peculiar motion of galaxy clusters moving in a specific direction at speeds that cannot be fully explained by the gravitational influences of surrounding cosmic structures, challenges current models of cosmic behavior. Scientists have proposed that there may be unseen forces at work, possibly massive structures lying beyond the observable universe, pushing these clusters in ways that we do not yet understand. The implications of dark flow are profound. If these movements are indeed caused by objects or forces outside our observable universe, it would force us to reconsider our entire framework for understanding the cosmos. For decades, the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales, has been a cornerstone of our understanding of the cosmos. But the existence of dark flow raises the possibility that the universe may not be isotropic after all. Perhaps there are vast, unobservable regions of space that contain massive structures influencing the behavior of galaxy clusters in ways that we had not previously imagined. This would radically challenge our assumptions about the large-scale structure of the universe, and could lead to new theories about its formation and evolution. As scientists continue to investigate these strange motions, dark flow could open up a new frontier in cosmology. It encourages researchers to look beyond the observable universe and consider the possibility that there is much more out there than we can currently detect. The discovery of such unseen structures could lead to a redefinition of the universe's evolution and its ultimate fate. Finally, there is the question of the universe's future, an inquiry that remains both deeply speculative and critically important. The role of dark energy in driving the accelerated expansion of the cosmos remains a central question, and understanding its nature could help scientists predict the future trajectory of the universe. If dark energy is a constant force, the universe will continue to expand indefinitely, but if it changes over time, its effects could be dramatically different. Theories about the ultimate fate of the universe abound. Will the stars burn out, leaving the universe cold and dark? Or could the universe eventually collapse back on itself in a big crunch? Such theories are more than just intellectual exercises. They speak to humanity's deepest questions about the nature of time, space, and existence itself. These questions, and countless others, continue to drive both scientific inquiry and imaginative exploration. The mysteries of the cosmos, from the behavior of cosmic rays to the fate of the universe, remain a vast and fertile ground for discovery, one that promises to keep us searching for answers for generations to come. The universe, in its boundless complexity, continues to present profound challenges to our understanding, pushing the boundaries of science and imagination alike. One of the most tantalizing frontiers is the intersection of gravity and quantum mechanics, an area of study that raises profound questions about the nature of existence itself. At the heart of this enigmatic dance lies the question of black holes, those dark, mysterious entities whose formation and eventual fate remain shrouded in uncertainty. Scientists are deeply engaged in an ongoing investigation to determine whether the information that falls into a black hole is truly lost to the cosmos, or if it can somehow be recovered. The introduction of the holographic principle, suggesting that the entire universe may be encoded on a distant two-dimensional surface, has sparked debates that could radically shift our understanding of both black holes and the fundamental laws that govern the universe. This paradox concerning information preservation challenges the very fabric of physics, offering the possibility of a breakthrough in our quest to decipher the universe's deepest mysteries. But even more profound questions linger in the cosmos, like whether the universe will ultimately experience a rebirth or undergo cycles of inflation and collapse. The concept of cyclic cosmology, the hypothesis that the universe may go through an eternal series of expansions and contractions, opens up tantalizing possibilities. Could our universe, like a phoenix, rise again after its inevitable demise? Or will it collapse into a singularity, only to be reborn in another cosmic cycle? Such speculative models invite both theoretical and observational exploration, inviting scientists to probe the very limits of space and time. The ongoing evolution of technology and the expansion of observational capabilities ensure that this quest to understand the mysteries of the universe is far from complete. With each passing year, new discoveries push the boundaries of our knowledge, and what was once thought to be impossible becomes ever more tangible. One of the most significant tools at our disposal in this pursuit of cosmic understanding is the quasar, those incredibly luminous objects that offer critical insights into the nature of the universe. Powered by supermassive black holes at the centers of distant galaxies, quasars are among the brightest objects in the universe. Their light, which travels across vast cosmic distances, allows scientists to peer into the past, offering glimpses of the early universe and the formation of galaxies. As these cosmic beacons emit light across billions of years, they provide a unique opportunity to study the expansion of the universe. By analyzing the redshift of quasar light, astronomers can calculate how fast quasars are receding from us, offering vital clues about the rate of cosmic expansion at various points in time. But the importance of quasars does not end with the study of the universe's expansion. These powerful objects also allow us to probe the conditions of the universe when it was still in its infancy, just a few 100 million years after the Big Bang. Observing quasars that existed at this early stage of the universe's evolution gives researchers critical insights into the formation of galaxies, black holes, and other cosmic structures. The energy emitted by quasars reveals the presence of surrounding gas and dust, shedding light on the intergalactic medium and its role in the formation of stars. In addition, the study of quasars is integral to refining and developing our understanding of fundamental cosmological principles, as they enable astronomers to test existing theories and develop new models for explaining the complex interactions of matter, energy, and gravity. Each quasar, in its brilliance, holds a piece of the cosmic puzzle, offering a vital clue in the story of the universe's origins and its continuing evolution. Similarly, the cosmic microwave background, CMB, the afterglow of the Big Bang, serves as a snapshot of the universe when it was just 380,000 years old, carrying essential information about its early composition and structure. However, many mysteries still surround the CMB, particularly the anisotropies, or variations in temperature across the sky. While scientists have mapped these temperature fluctuations in remarkable detail, their precise origins remain an area of active investigation. One of the central questions involves the relationship between these anisotropies and the clumping of matter that eventually led to the formation of galaxies and large-scale cosmic structures. Additionally, the polarization of the CMB provides clues about the processes that occurred in the universe's infancy, particularly regarding gravitational waves generated by inflation, the rapid expansion of space that took place just moments after the Big Bang. Detecting the faint signals from this polarization is an incredibly challenging task, but as technology advances, scientists are optimistic that these patterns will help unlock deeper insights into the universe's evolution and the fundamental forces that shaped its creation. There are also ongoing debates surrounding the presence of cold spots and hot spots in the CMB, with some suggesting that these anomalies could be the result of large-scale cosmic structures, such as superclusters or voids. Others have speculated more exotic explanations, including the possibility of interactions with other universes. Such discussions reveal just how much remains unknown about the cosmos, underscoring the complexity and wonder of our universe. Meanwhile, scientists continue to probe the universe's overall composition, using CMB data to deduce that a staggering 72% of the universe consists of dark energy, while only 4% is made up of ordinary matter, and 24% is composed of dark matter. Understanding the roles that these mysterious components play in shaping the cosmos remains one of the greatest challenges in modern astrophysics. One of the most fascinating aspects of this cosmic puzzle involves the study of dark galaxies, enigmatic cosmic structures that are believed to contain vast amounts of dark matter but very little visible matter. These elusive galaxies are difficult to detect using conventional astronomical techniques, which typically rely on visible light. However, by pursuing these hidden entities, astronomers can unlock important insights into the nature of dark matter, which constitutes approximately 27% of the universe's mass energy content. The study of dark galaxies provides crucial clues about the formation and evolution of galaxies in general, as the presence of dark matter plays a pivotal role in shaping the growth and interaction of galaxies over cosmic timescales. By understanding how dark matter influences the formation of galaxies, scientists hope to gain a deeper understanding of the gravitational effects of dark matter and how it shapes the large-scale structure of the universe. Through all of these investigations, the study of quasars, the exploration of the CMB, and the pursuit of dark galaxies, scientists are steadily piecing together the intricate story of the universe. With every breakthrough, we inch closer to understanding the true nature of the cosmos and the fundamental forces that govern it. As technology improves and our observational tools become ever more powerful, the mysteries of the universe become more accessible, offering tantalizing glimpses into the origins, evolution, and ultimate fate of everything that exists. The investigation of dark galaxies provides a crucial piece of the puzzle in our quest to understand the universe. These mysterious and largely unseen galaxies are key to solving the riddle of missing baryonic matter, the kind of ordinary matter that forms stars, planets, and galaxies. While we can observe the luminous components of galaxies with ease, The majority of matter is thought to be hidden in the form of diffuse gas that resides within dark galaxies. Understanding these elusive entities brings us one step closer to uncovering the true nature of baryonic matter and its role in cosmic evolution. As astronomers refine their observational techniques and technology, they are edging closer to detecting these subtle signatures of dark galaxies. Methods like gravitational lensing, deep imaging surveys, and data gathered from advanced telescopes contribute to this ongoing effort. Each discovery not only illuminates the characteristics of dark galaxies, but also deepens our understanding of the fundamental workings of the universe, revealing just how much we still have to learn about the vast cosmos we inhabit. Gravitational wave astronomy has introduced a groundbreaking way to explore space. This field of study is revolutionizing our understanding of the cosmos by revealing phenomena that were once invisible to traditional electromagnetic observations. When massive objects like black holes or neutron stars collide, they create ripples in the fabric of space-time that travel across the universe. Detecting these gravitational waves gives scientists the unique ability to observe these events and study the behavior of matter under extreme conditions, offering a glimpse into the nature of the universe that was previously out of reach. One of the most intriguing puzzles revealed by gravitational wave astronomy is the nature of black hole mergers. Before the advent of gravitational wave detection, our knowledge of black holes was based primarily on indirect evidence. But with new data, scientists have uncovered black holes that are much larger than we previously thought, suggesting a more complex relationship in their formation and evolution. These findings raise important questions about how these massive objects form and what role they play in the structure of the universe itself. In addition to black hole mergers, the detection of gravitational waves has opened the door to a deeper understanding of neutron star collisions. When two neutron stars collide, they not only produce gravitational waves, but also emit massive amounts of electromagnetic radiation, including gamma ray bursts. By studying these events, scientists can investigate the elements produced in these cataclysmic collisions, providing vital clues about the origin of heavy elements in the universe. This multifaceted approach to cosmic observation reveals interconnected narratives and exposes the gaps in our current understanding of the universe. Gravitational wave astronomy also intersects with fundamental concepts in physics, such as Einstein's theory of general relativity. While general relativity has held up under scrutiny for over a century, some of the unexpected properties of gravitational waves suggest that there may be unknown aspects of gravitation yet to be discovered. These findings challenge our current models, suggesting that our understanding of stellar evolution and the fabric of space-time may need refinement. This evolving field is reshaping our view of the cosmos and prompting scientists to rethink long-standing theories, exploring new avenues of research that could change the way we understand the universe. Neutrinos, often referred to as the ghost particles of the universe, may seem elusive due to their incredibly small mass and neutral charge, which cause them to interact very weakly with matter. However, despite their elusive nature, neutrinos hold profound significance for our understanding of the cosmos. By studying these particles, scientists can delve into the processes that occur at the core of stars, including our own sun, revealing the mechanisms by which these celestial bodies generate energy and produce elements. One fascinating aspect of neutrinos is their sheer abundance. Trillions of neutrinos pass through the human body every second without us noticing. Most of these particles come from the sun, traveling through space at nearly the speed of light. By detecting these elusive particles, researchers can build a detailed picture of solar processes and even confirm long-standing theories regarding the generation of solar energy. This understanding is crucial not only for astrophysics, but also for advancing technologies related to energy production on Earth. Beyond their role in stellar processes, neutrinos are produced in some of the most violent and extreme cosmic events, such as supernovae, neutron star mergers, and the formation of black holes. Observatories designed to detect these particles allow scientists to study the remnants of these grand explosions. The data gathered from neutrino detection offers valuable insights into the evolution of the universe and the elements that make it up, providing a clearer picture of the processes that govern the formation and destruction of matter. The study of neutrinos is also critical for understanding one of the universe's most elusive mysteries: dark matter. Dark matter is believed to make up about 27% of the universe, yet it remains invisible to conventional detection methods because it does not emit, absorb, or reflect light. Neutrino research could provide vital clues to unraveling the nature of dark matter, shedding light on this mysterious substance and the very fabric of the universe. In this sense, the study of neutrinos is not just a niche pursuit, but a vital component of the ongoing quest to unlock the universe's most profound secrets. The study of dark matter itself is poised to reshape our understanding of the cosmos and our place within it. Despite its overwhelming presence, dark matter remains incredibly elusive, invisible to our current means of observation. However, its influence on the behavior and structure of galaxies is undeniable. Advancing our knowledge of dark matter could not only revolutionize our understanding of the fundamental forces that shape the universe, but also spark technological innovations that could have a profound impact on human civilization. Historically, breakthroughs in science often arise from our quest to understand the universe, and the study of dark matter is no exception. Just as the development of satellite technology was driven by our understanding of gravitational forces, so too could new technologies emerge from dark matter research. These advances might lead to innovations in communication, transportation, and even energy production, bringing us closer to realizing possibilities that we have yet to imagine. As we continue to study the cosmos, from dark galaxies and gravitational waves to neutrinos and dark matter, we uncover new connections between the tiniest particles and the vast, unseen structures of the universe. Each discovery brings us closer to a deeper understanding of the fundamental principles that govern all of existence, offering the promise of new technologies and new perspectives on our place in the universe. As we uncover the secrets of the universe, particularly the elusive nature of dark matter, we are faced with more than just scientific discovery. We are confronted with profound philosophical and existential questions. The study of dark matter pushes humanity to reflect on its place in the cosmos, sparking a collective contemplation of our existence and the very nature of reality itself. With each new piece of the puzzle, our understanding of the universe deepens, inviting us to question long-held beliefs and assumptions. Are we, as individuals and as a species, significant in a universe that stretches across unfathomable distances and harbors untold mysteries? This growing knowledge could serve to foster a more profound sense of interconnectedness among people, as we come to realize that we are mere specks in the vast, intricate web of the cosmos. The more we learn about the universe's grand design, the more we recognize our shared fragility. This realization could inspire a shift in perspective, urging us to acknowledge that our lives and experiences are interconnected, not just with those around us, but with the very fabric of the universe itself. Humanity, in all its diversity, would be reminded that it is a small part of something much greater. Such a perspective shift has the potential to unite people across borders, transcending differences of culture, language, and history. The pursuit of knowledge about dark matter, for example, has already led to international collaborations with scientists and researchers from across the globe coming together in a shared quest to understand the universe. These partnerships are a testament to the power of collective action in the face of the unknown. By working together, nations can overcome the limitations of individual pursuits and harness the collective intellectual and technological resources needed to solve some of the universe's most profound mysteries. The shared endeavor could help cultivate a deeper appreciation for science, ultimately nurturing a spirit of global cooperation. At its heart, space exploration is about much more than uncovering the unknown. It offers critical insights into the very nature of life itself. For millennia, humans have grappled with questions about our place in the cosmos, contemplating whether life is unique to Earth or whether other forms of life exist beyond our planet. As we observe exoplanets in distant galaxies, particularly those situated in the so-called habitable zone, we are confronted with the realization that the conditions necessary for life may not be as rare as once thought. This understanding challenges the long-held belief in human exceptionalism, inviting us to reconsider our role in the broader scheme of things. The discovery of microbial life in extreme environments here on Earth further supports this idea, suggesting that life could thrive in conditions once thought inhospitable. It expands the boundaries of what we once considered possible, prompting us to rethink where else life might be found, whether on other planets, moons, or celestial bodies. These findings encourage a more open-minded approach to the search for life beyond our own planet, pushing humanity to explore areas once dismissed as barren or uninhabitable. In parallel, the study of cosmic phenomena like supernovae, black holes, and gamma-ray bursts reveals the dynamic and ever-changing nature of the universe. These powerful events not only shape the galaxies over billions of years, but also remind us of the fragility of existence. The explosive forces of a supernova, for example, mark the end of a star's life. Yet this violent event is also the birth of new elements, feeding the very processes that create life. Such occurrences underscore the delicate balance that allows stars to ignite and systems to evolve. This cosmic dance of destruction and creation offers a humbling perspective on our own existence, emphasizing how fleeting and transient our time in the universe truly is. As humanity delves further into the mysteries of dark matter and dark energy, we encounter an even more elusive unknown. These substances, which make up much of the universe's mass, remain largely a mystery. Their discovery is a reminder of how little we understand about the cosmos, despite our advances in technology and observation. Each new finding invites reflection on our place in the grand scheme of things, encouraging us to embrace the unknown rather than fear it. The search for knowledge becomes not just about uncovering the secrets of the universe, but also about understanding who we are and where we fit within this vast, interconnected expanse. Yet the pursuit of space exploration is not without its challenges. Space phenomena, such as asteroid impacts or solar flares, pose real risks to Earth, reminding us of our vulnerability in the face of an unpredictable and sometimes hostile universe. For instance, asteroid impacts have shaped Earth's history before, with catastrophic consequences that have altered the course of life on our planet. The most famous example is the asteroid that struck Earth some 66 million years ago, leading to the mass extinction of the dinosaurs. While such events are rare, they serve as a stark reminder of our planet's fragility. The threat of cosmic events, such as asteroid collisions, supernova explosions, or gamma-ray bursts, also forces us to reconsider how we view the environment on Earth. These events can influence planetary atmospheres and disrupt ecosystems, offering scientists a broader lens through which to understand the delicate balance that sustains life on our planet. By studying the potential impact of such events, we gain a better understanding of the conditions that make life possible on Earth and how those conditions might be threatened by forces beyond our control. These cosmic phenomena often inspire collaboration across disciplines. Astronomers, climate scientists, and geologists come together to explore how past cosmic events may have influenced climate changes or mass extinctions. This multidisciplinary approach not only deepens our understanding of Earth's history, but also helps us build a more accurate picture of how the universe interacts with our planet. As we study these phenomena, we uncover the intricate web of connections that bind the Earth to the cosmos. In response to these dangers, space exploration has become more urgent than ever. The detection of cosmic threats, such as asteroids or supernovae, requires both scientific expertise and international cooperation. The need to monitor the skies and develop strategies for planetary defense has never been more pressing. As we invest more resources into understanding these potential threats, we also cultivate a deeper appreciation for the delicate balance that sustains life on Earth. The possibility of catastrophic cosmic events raises fundamental questions about how we as a global community would respond to such a crisis. How would nations collaborate in the face of an existential threat? How would governments and societies adapt to the challenges posed by such events? These questions force us to rethink how we approach global governance and the role of international cooperation in safeguarding humanity's future. A global crisis resulting from a cosmic disaster would likely require unprecedented international collaboration. Nations would need to pool their resources, share knowledge, and act together to protect the planet. This would mark a profound shift in global governance, as countries traditionally focused on their own interests would now have to prioritize collective security and survival. Such cooperation could lead to the establishment of global frameworks aimed at planetary defense, setting a new precedent for how nations work together to address global challenges. In the aftermath of such an event, new power dynamics could emerge. Areas of the world most affected by the disaster might struggle for resources, while other regions could attempt to exert influence over the recovery process. This could lead to shifts in political power and governance structures, with decentralized or new governing bodies emerging to manage the crisis. Governments may need to rethink their authority, effectiveness, and priorities as they work together to rebuild and ensure the long-term resilience of humanity. The aftermath of a catastrophic event would also require a reevaluation of priorities. The focus would shift toward environmental restoration, economic stability, and public health, pushing governments to reconsider their development strategies and policies. In the face of such challenges, global cooperation could become even stronger, with nations united in their shared quest for survival and resilience. Ultimately, the threat of cosmic events could be a catalyst for profound change in the way humanity approaches global governance and international relations. The realization of our vulnerability in the face of forces beyond our control might foster a sense of unity, urging governments to collaborate more closely in the pursuit of stability and security. Such cooperation could mark a significant evolution in the way nations engage with each other, leading to a more unified world that recognizes the shared responsibility of protecting our planet and the future of our species. Documentaries focusing on space and cosmic discoveries play a crucial role in raising awareness about these existential threats. By presenting scientific research and expert analyses in an accessible and engaging way, these films help to illuminate the potential risks that exist beyond our planet. Through vivid visuals and compelling narratives, they convey the magnitude of cosmic events, such as asteroid impacts, solar flares, and gamma-ray bursts that could affect life on Earth. These documentaries serve not only to inform the public about the dangers lurking in space, but also to inspire curiosity and action. By showcasing past events, such as the asteroid strike that contributed to the extinction of the dinosaurs, these films highlight the relevance of cosmic threats to our lives. They remind us that the risks we face today are not hypothetical, they are real, and they have shaped the history of our planet. In addition to examining past events, documentaries often highlight current research and technology aimed at monitoring and mitigating these threats. Through interviews with scientists and space agencies, viewers gain insight into the efforts being made to protect our planet. Initiatives such as planetary defense strategies are explored, shedding light on the innovative technologies and international cooperation needed to safeguard humanity from cosmic hazards. When done well, these documentaries can spark public interest in space exploration and the study of cosmic threats, driving support for further research and funding. By making complex scientific concepts accessible and engaging, they help to create a sense of collective responsibility for the future of our planet and the preservation of life as we know it. Reports of potentially dangerous cosmic discoveries often elicit a complex mix of emotions. Fear and curiosity are natural reactions when confronted with the possibility of a catastrophic event, such as an asteroid collision or a supernova explosion. While fear reflects our instinctive concern for the safety of our planet, curiosity drives us to seek knowledge about these phenomena. People wonder how likely these events are, what scientists are doing to prevent them, and what we can learn about the universe from studying them. This combination of fear and curiosity deepens public interest in cosmology and astrophysics, prompting individuals to engage more deeply with scientific discourse and exploration. It encourages people to seek answers to fundamental questions about the nature of the cosmos and our place within it, all while cultivating a greater sense of shared responsibility for the future of humanity. The discovery and exploration of the universe can evoke emotions ranging from awe to wonder as humanity comes to terms with the incredible forces that shape the cosmos. The sheer awareness that such monumental celestial phenomena exist far beyond the scope of our daily lives has the potential to inspire a profound appreciation for the vastness of space and our place within it. In the face of these cosmic forces, despite the inherent dangers they pose, we find ourselves reminded of the extraordinary nature of our existence. This realization often sparks reflection on the interconnectedness of life on Earth and the universe as a whole. For many, the thought that we are merely one part of something so much larger than ourselves is humbling. Yet, it can also serve as a source of motivation, compelling us to strive for a deeper understanding of the universe and our role in it. It is a powerful reflection that, no matter how vast or complex, we are connected to the mysteries of space. This blend of awe, curiosity, and humility tends to prompt collective responses from society. People often come together to discuss preventive measures or to support scientific initiatives that aim to mitigate the risks posed by cosmic events. This sense of unity may manifest itself in increased public interest in space exploration, greater funding for planetary defense, or the collective will to understand more about the universe and how we can protect ourselves from its potential threats. The resulting sense of community that arises from our fascination with the cosmos can be both inspiring and comforting. In a world often divided by borders and politics, the exploration of the unknown creates a shared vision, where humanity is united in its pursuit of knowledge. This collective drive towards understanding the universe is not only driven by scientific curiosity, but also a deep-seated desire to safeguard our future. With the possibility of catastrophic cosmic events like supernovae or gamma-ray bursts looming over us, society increasingly recognizes the urgency of preparing for such threats, just as we must protect our planet from more immediate environmental dangers. When we delve into the study of extreme cosmic phenomena, we are offered a stark reminder of both the power of the universe and the vulnerability of life on Earth. Events like supernovae, which can outshine an entire galaxy in a brief moment, serve as a vivid metaphor for the fragility of our planet. Just as a supernova can disrupt the balance of the universe, our actions on Earth, from unchecked industrial growth to deforestation, threaten to disrupt the delicate balance of our ecosystems. These cosmic events, while vast and seemingly distant, provide a perspective on the nature of destruction. They challenge us to consider the irreversible damage that can occur not just on a planetary scale, but on a cosmic one, urging us to reflect on how human activity can lead to similar cataclysms. One of the most unsettling aspects of studying the universe is the realization that many of these cosmic events occur on timescales that far exceed the length of human history. The potential consequences of a nearby gamma-ray burst, for example, could be catastrophic for all life on Earth. The time scale involved in these events serves as a sobering reminder of the immediacy of the challenges we face, from climate change to the degradation of biodiversity. It's a call to action, urging humanity to act now, before it is too late, much like the explosive forces that drive the stars themselves. The closer we come to understanding the immense power of cosmic events, the clearer it becomes that we must take immediate steps to protect our planet from both natural and human-induced threats. By drawing these parallels between the cosmic and the environmental, we are given a sense of urgency that transcends scientific discovery and enters the realm of responsibility. Just as a star reaches its critical threshold and explodes, so too must we reach a point where action becomes no longer a choice but a necessity. In this sense, the understanding of the universe and its vast forces not only deepens our sense of the unknown, but also increases our awareness of the fragility of our own existence. At the same time, space exploration has dramatically shaped our technological landscape in ways that continue to influence nearly every aspect of modern life. From the early milestones of space exploration, such as the launch of the first artificial satellites, we have seen technological innovations that have transformed communications, navigation, and countless other industries. Satellites, which govern everything from weather forecasting to global broadcasting, are just one example of how discoveries in space have led to significant breakthroughs in technology that touch all corners of our daily existence. The scientific advancements made through the study of space have proven invaluable, not just in expanding our knowledge of the universe, but in fostering new technologies to explore and understand it more thoroughly. The materials developed for spacecraft, for example, have found their way into the consumer market, leading to improvements in fire-resistant clothing, lightweight building materials, and more. These breakthroughs have far-reaching implications that extend well beyond their initial purpose, demonstrating how scientific exploration can fuel technological progress across diverse sectors. Furthermore, our understanding of celestial bodies and their environments has had significant applications in fields like geology, environmental science, and climate modeling. By studying planetary atmospheres and surface conditions, we gain insights that can help us better understand the challenges facing Earth. Technologies developed for space missions have had transformative effects on our approach to understanding not just the stars, but the very planet we call home. Perhaps most notably, the pursuit of space exploration has brought nations together in a shared endeavor for knowledge and discovery. Collaborative projects such as the International Space Station exemplify the power of cooperation in advancing scientific progress. By pooling resources and expertise from around the world, these projects have led to innovations that might never have been possible without such collective efforts. In this way, the quest for space exploration has not only expanded our understanding of the universe, but also reshaped the way nations interact and collaborate on global challenges. As humanity continues to push the boundaries of space exploration, the technological advancements that result from these efforts will undoubtedly reshape our global landscape. From revolutionizing our approach to environmental conservation to driving advancements in renewable energy, the knowledge and systems developed in the pursuit of understanding space will leave an indelible mark on the way we live, work, and protect our planet for generations to come. Through the shared pursuit of knowledge, the exploration of the cosmos stands as a beacon of possibility, guiding us toward a future where humanity can rise to meet the challenges of both space and Earth with unprecedented unity and innovation. The exploration of Mars and the discoveries surrounding it have sparked a profound sense of wonder and curiosity, fueling dreams of human colonization on this distant red planet. These discoveries not only inspire visions of future human settlements, but also point toward the critical technologies necessary for survival in environments that are far harsher than anything we experience on Earth. As scientists and engineers continue to pursue sustainable life support systems, advanced robotics, and other technologies for extraterrestrial exploration, they inadvertently unlock innovations that could significantly enhance life on Earth as well. Every discovery made in space exploration does more than reveal the universe's vastness. It serves as a catalyst for human progress. These revelations push the boundaries of human ingenuity, driving us to imagine new possibilities and develop the tools needed for future ventures beyond our planet. As we continue to explore the cosmos, we begin to realize that these advances, while initially aimed at solving challenges in space, can often have applications that ripple back here, improving technologies and systems we rely on daily. The stories of space exploration transcend beyond mere tales of missions and technological breakthroughs. They are powerful narratives that ignite the imagination, especially in younger generations. When we recount the heroics of astronauts who venture into the unknown, or the dedication of engineers who design spacecraft capable of withstanding the extreme conditions of space, we celebrate the human spirit's innate curiosity and drive to explore. These narratives serve as proof that daring to dream big can lead to extraordinary achievements, inspiring countless young minds to pursue careers in science, technology, engineering, and mathematics, STEM. Take, for instance, the Apollo missions. These monumental feats of human achievement marked the first time that humanity set foot on the moon, a moment that not only showcased unparalleled ingenuity, but also united the world under a shared sense of accomplishment. The ripple effect of this historic event continues to influence generations today. The legacies of the Apollo missions live on, as they have ignited further curiosity and ambition, now channeled into missions targeting Mars and beyond. Each new story of space exploration is a reminder that collaboration and teamwork are key elements in overcoming the most daunting challenges, values that are just as crucial when addressing the issues we face here on Earth. Moreover, the technological advancements made possible through space exploration have proven to be far-reaching in their impact. Innovations such as satellite technology have transformed global communication, revolutionized weather forecasting, and enhanced our ability to predict natural disasters. The breakthroughs made in materials science and medicine as a result of space research have led to new tools and techniques that improve daily life for millions. These advancements underscore a timeless truth. Space exploration is not just about the quest for knowledge. It is also about creating tangible benefits for humanity. When we share these stories of exploration, we help create a sense of connection to something much larger than ourselves. They serve as a source of hope and ambition, motivating young hearts and minds to chase dreams that seem impossible. In telling these tales, we not only educate, but also inspire future generations, who may one day stand among the stars, continuing the work of those who came before them. By framing our exploration efforts within engaging narratives, we offer more than just knowledge. We offer a vision of a future filled with possibility and promise. As humanity ventures further into the cosmos, the dual nature of space becomes more apparent, both awe-inspiring and terrifying. The vastness of the universe, with its unknowns and potential dangers, presents a challenge unlike any other. Preparing for this adventure requires a multifaceted approach, one that encompasses education, technological innovation, and the cultivation of a collective sense of curiosity. By promoting scientific literacy and fostering a greater understanding of the universe, we equip individuals with the tools to confront the challenges of space exploration with informed, open minds. Knowledge reduces fear, allowing us to face the unknown with confidence and resilience. Advancements in technology play a critical role in humanity's ability to explore these uncharted territories. Developing robust spacecraft, sophisticated instruments, and reliable life support systems is essential if we are to venture further into space, facing environments that are as unpredictable as they are dangerous. Missions to Mars and beyond will require not only cutting-edge engineering, but also the ability to adapt quickly to new and unforeseen challenges. With each step we take, we are not only discovering new worlds, but also developing the skills and technologies needed to thrive in them. At the same time, it is essential to cultivate a mindset that embraces exploration and uncertainty. We must foster curiosity and resilience in the face of adversity, whether it comes in the form of technical failures or the psychological toll of long-duration space missions. History is filled with examples of explorers who face setbacks and obstacles, yet they overcame them through adaptability and a willingness to learn from mistakes. As we venture deeper into space, we must be mentally prepared for encounters that may be unsettling or even overwhelming. Another crucial element of our space exploration endeavors is international cooperation. As the challenges of space become more complex, the need for global collaboration grows. The vastness and complexity of the cosmos require a collective effort, one that transcends national borders and political differences. By fostering international partnerships, we create a unified front capable of tackling the many challenges that lie ahead. This shared vision of exploration can inspire wonder and awe, transforming what may seem like an intimidating unknown into a collective opportunity for discovery and growth. Ultimately, the journey into space is not just about preparing for what we may find, but embracing the unknown with open arms. It is about developing the tools, technologies, and mindsets necessary to confront challenges head-on. By weaving these experiences into engaging narratives, we not only inspire, but also empower the next generation to continue humanity's legacy of exploration, pushing the boundaries of what is possible. Through curiosity, innovation, and cooperation, we can turn the vast and mysterious cosmos into a realm of opportunity and discovery for all.